Hello everyone, I'm teacher Xie. The unit we are doing today is the mechanism drawing and simulation. In this unit, we will be using a computer for mechanism drawing and simulation. Why do we need to do it this way? There are several reasons. First, during the design phase, we can concretize our drawings. Let's take a look over here. Using the software, Solid Edge, we can technically expect it, mechanism design, and assemble them together. After drawing it, you can discuss with your partner, classmate, or teacher about the purpose of your mechanism and what objective it's trying to achieve. The most important thing is that we can use the computer to perform motion simulation. For example, we can use the drag function and select the component we want to drag. And we choose the free move mode, then it can perform a vertical movement. This way we can know what its location and its highest and lowest is, to confirm whether our design can meet our requirements. Let me briefly explain our following lesson outline. First, we will draw the 2D sketch. Before we begin with 3D modeling, we must start with the 2D sketch drawing. After drawing it, we will give it some height and thickness, and it will become a 3D solid. Afterwards, we will perform assembly and modification. We will check if the assembly meets our expectations. When it's done, we will move on to checking if there are parts that are causing interference during the assembling process, but we did not notice. We can use the software functions to check. Next, we will perform simulation on the moving mechanisms and see if they can meet our expectations. Finally, if our mechanism design functions meet our requirements, we will produce what's called engineering drawings, then see if we are going to do handcraft production or digital manufacturing, such as laser cutting or 3D printing, to produce and assemble our design. In this course, the software we'll be using is called Solid Edge. An educational version of the software is available for use. If you need it for practice, you can apply for it in this website. When you enter the website, at the top shows Solid Edge International Certification Student Trial Version Application. Scroll down to the very bottom. There is a form to fill in. You must complete the information that is required with seriousness, because the information will be reviewed later, so you can apply here for the student edition if you need it. After installing the software, a shortcut will appear on the desktop. You can also go to the Start button. Click on it and search for Solid Edge. There are a couple of choices over here. And we will choose Solid Edge 2019. We can double click to open it. After it opens, the recently opened files will be shown here. Let's start by creating a new drawing. There are different types of files. For this course, we will be using the isometric part, the assembly and the engineering drawing. The other types of files such as sheet metal and welding won't probably be used. First of all, let me explain that. When using this software, each component part will be drawn individually and then assembled together. So we need to draw our components first in order to assemble them together. First, let's click on the isometric. Part. When it loads, the screen will look like this. Let's go back to the previous page. Click on this application icon, and you can go back to the screen at the beginning. We can click on New. There will be some options for a new drawing. Click on it to view them. Once you click it, you have all these different templates. Within our options, we choose the isometric part. Here you can find the part templates used in different countries. In our course, we'll mainly use isometric parts. so we won't be selecting all the choices. If you need to use other standards, you can find them here. We won't choose this. Click on Cancel to go back to the new part file. Let's take a look at this. Let's first take a look at the screen. There are a few things to explain. The first thing is that on the top right corner, there is this application icon. When you click it, you will return to the initial screen, and you can choose other functions, such as open file, print, 3D printing, or to bundle output. All this is done from this menu on the left. Click on the application icon to go back to this screen. Most of our work will be carried out in this screen. All the commands will be grouped into ribbons based on their functions. For example, when we want to draw a sketch, we will select this part. For service processing, we will go this ribbon. If we want to set the PMI, we go to this ribbon. All these functions will be divided and grouped into ribbons. Most of the time, we start from using some of the commonly used commands in the home ribbon. When we move the cursor over, each command will have a simple description, and it can also display some animations. If you're not familiar with a command, move the cursor over, hold it for a little bit, and a pop-up description box. If you have any questions, you can click on F1. And it will open a website where you can browse, and it will give you a detailed explanation of the commands. Let's close this. Let's continue. Next. There's a command bar. For example, after I select the line command, a command bar will appear. This command bar will display the detailed settings for this command. After I select a command, some instructions regarding this command will be shown at the bottom. In this case, you need to click on the first point. What does it mean? When you are using this command, you first need to confirm where this first point will be. When I select a command, the command bar will appear, and instructions will be shown at the bottom telling you what this command's next step is. At the lower right corner of the screen, there is the Quick View Cube. Let's say an object has 6 sides: the front, the top, the left, and so on. You can use this cube to quickly browse the list views. This function will be used very often during our operation. We'll briefly explain for now. We'll go over it more during our operation. Next, let's talk about our preliminary practice exercise, which is the solid edge 2D sketch drawing. Let's see how the 2D sketch drawing is performed. On this screen, there are some sections that we will be using. The first one is the commands related to sketching in here. The next ones are the options to establish the relationship between the entities. On the far right is the command to indicate the dimensions. The bad thing about this software is that when we're sketching, we can modify the dimension at all time to meet our design needs. We will design a simple triangle. Let's practice a bit. We're going to draw a right triangle. Before we begin drawing, although we are drawing inside a 3D space, we'll start from 2D. When we are at a certain view, we can use this Quick View Cube to change views. You can click on this house icon to go back to the initial view. You'll see that there are 3 axes: the x-axis, the y-axis, and the z-axis. This represents the 3 dimensions of space. First, let's select our command. We'll choose the line to perform our 2D drawing. Let's select the line command. As explained to you earlier, we'll be drawing in 2D first, so we need to confirm which plane we will be drawing on. Let's confirm which plane we are going to draw this picture on. For example, when I move my cursor over, let me zoom in. When you move the cursor here, a padlock icon will appear on the XZ plane. It means that when we are drawing, we'll begin drawing from the XZ plane. You can also go to here, the XY plane, or move to here, to the YZ plane. So you need to confirm first on which plane you will draw the 2D sketch. We can think like this. We will draw based on our habit. Of course, if you have no other habits, that's okay. Follow my steps first. I will first use the quick view cube and click on the top view where I will draw the sketch. We'll draw the sketch using the top view. When drawing this, let me tell you of an action. When we are changing the views, for example, if we want to zoom in and out, we will use the scroll wheel to perform this action. Since we haven't drawn anything yet, you can't see how this function is working. The second action is to press and hold the scroll wheel at the middle and move the cursor up and down. You'll notice that our drawing will begin to move. Regarding the third action, if you want to pan, press and hold the scroll wheel and then press and hold the shift key. Then you can perform the pan movement. You can practice a little bit. Let's review the third actions. The first one is the scroll wheel for zooming. You can scroll up and down to zoom in or out of this view. The second one is to press and hold the scroll wheel to tell the object that is without pressing the shift key. Move the cursor up and down, and you can perform the tilt movement. If you press and hold the shift button and the scroll wheel, you can perform a pan movement. Let's practice this part. After practicing the movements, using the scroll wheel, let's close this file first, because during its operation, you may have modified the original environment settings in order to make it more convenient during operations and have no problems. We'll close this file and create a new drawing again. We'll select isometric part. We are in a new environment, so your settings are the same as mine. Let's begin. The drawing of the right triangle. We'll select the line command. When selecting the line command, these words will appear at the hint bar. On the hint bar, it will instruct you to choose the first point. Before clicking, notice that when you move the cursor over here, a padlock will appear as mentioned earlier. This padlock means to lock onto a plan. We want to, so we will lock onto the XY plan. So we will lock onto the XY plan. There are two ways to lock on. The first one is to press F3 when it's at this state, and the padlock will disappear. The right side of the screen will show an F3 icon. What does this mean? I'm already locked onto this plan. If this plan is not the one you want, press F3 again. We can click on the icon with the mouse, or press F3 and it will disappear. When you move the cursor to the coordinate axis, the padlock will appear. You can press F3 or use the cursor to press the F3 icon. They will both have the lock onto plan effect. Once we are confirmed to draw on the XY plan, we'll perform the next step, which is to click the first point. We can use the scroll wheel to enlarge the top view. After zooming in, press and hold the scroll wheel to move the drawing to the center. Next, we'll draw our sketch. Let's place the first point. When my cursor moves to the coordinate origin, a lollipop icon will appear, which means I'm going to lock onto this point. I've locked onto the 0 point location. Click on it and drag upwards. Notice that dimensions will appear. After they appear, you can input a value. For example, we want to draw a line that is 30 in length. Press enter and this length is confirmed. Next, let's look at the 90 on the right. The box showing the number 90. What does it represent? The angle. This is 90 degrees. The 90 degrees position is viewed with respect to the coordinate axis. Next, we will confirm the 90 degrees and press enter and the indicator will disappear. We need to confirm the next one. For the next line, we will input 6t in length. We can input 6t inside the box. After that, we want the angle between the hypotenuse and the vertical leg to be 60 degrees. But here it's showing negative 30 something degrees. How much should we input? We'll input negative 30 and press enter. Displays this angle. The angle we keyed in was negative 30 degrees. So the angle between the hypotenuse and vertical leg is 60 degrees. Next, we'll drag the line back. When you drag this back, you will notice that a lollipop icon will appear at this line segment. This sketch is now finished. You can practice drawing this sketch. After you finish drawing, we need to check if our drawing meets the dimension requirements. Here we have a Smart Dimension command. We can click on the Smart Dimension command. After selecting it, notice that the command bar is different. Let's click on this line segment. Hold and drag it. This is 30, is correct. This is 60. Then from here to here, we cannot mark the dimension. Why? You need to use this angle command to mark this dimension. So the dimension between here and here is 60, which meets the dimension requirements. Let's continue marking the dimensions. We'll mark this dimension. We need to switch back to Smart Dimension because the dimension marking is different. Click here, then this line with this line is different. Remember that the dimension marking is different for angle and length. After marking the dimensions, you will realize that some dimensions are in red while some are in blue. What's more peculiar is that when you were doing this, your drawing method were the same as mine. But the color of our dimension markings are different. Different colors represent different meanings. Let's take a look at this. Let's take a look at this. The red part means that the dimension has been locked by a number value. So it will have a padlock icon. I will show you later. If it's blue, it hasn't been locked, it's driven. What does being driven mean? Its dimension is determined by the other dimensions in red. Let's go back and check on our sketch. Let's take a look at the sketch. If I click on the dimension in red, left click on it, and this display will show. Notice that this display is locked. What does being locked mean? The dimension can be locked using a number value. When I change the value, for example, I change this to 40, press enter and it will become 40. Again, I left click on it. And when the dimension pops up, I change it to 30 and press enter. It will restore back. When you click on this one, the padlock that appears is unlocked. It is driven and is in an unlocked state. We call this unlocked state. I will change this number to 40 and press enter. You'll notice that the number did not change and also a line appeared below the number. What does it mean? It means that it cannot drive. Let's undo this. This represents its real dimension. Having a line underneath means that it's wrong. So this 60, 30, or 51.96, these numbers cannot be changed. If it is shown in blue, it cannot be modified. The reason why the color of your markings are different is because our order was different. Let me show you. I'll remove the 60. Then I will remove this dimension. Then I will remove the 30. I will mark these dimensions again. I will mark this length first. Notice that now it appears in red. What does it mean? the dimension of these two sections. For example, I'll change this to 50, then press enter. See, that can be changed. Let's undo this, Ctrl plus Z. After undoing this, let's mark this dimension again. Notice the 60. What does this mean? The hypotenuse length cannot be decided on its own. It will be defined by these two other dimensions to fulfill the Pythagorean theorem. You must know this concept when marking the dimensions. The order of the marking will decide which dimension will be driven, which one will be unlocked, and which one will be locked. You need to pay attention to it. Let's review it again. Let's review again. The dimensions in red are locked with a number value, so the length or angle will be determined by this number. The dimension in blue is unlocked by the number value. It is unlocked. This dimension is driven by the other dimensions displayed in red. You need to remember this concept because we'll be encountering this situation very often. So you need to pay attention to the red and blue markings. Hello everyone! In our last lesson, we have finished the 2D sketching. Next, we'll use the basic functions of 2D sketching, and then we will continue towards drawing our solid to become a 3D entity. The practice example that we'll be doing is a motor friend. Let's see what a motor friend looks like. Let's see what a motor friend looks like. This is the motor friend that we will draw. But before we start drawing, we need to know how to perform its dimension measurement. We need to know how to measure this in order to draw the motor frame. Let's have a look. We'll be using the calipers to perform our measurements. Let's see how the calipers is used. Let's use the wheel used with the TT motor to demonstrate. Next, I'll show you how to measure the motor frame. First of all, this is our caliper. It can slide and measure the dimension using the scaling displayed on top. Regarding how to read this, I will tell you later. First of all, let's have a look. We use this part to measure the outer diameter. You can slide this open and measure its outer diameter. When measuring, you can slightly slide it. When doing this, you must pay attention to this. This part of the caliper must be perpendicular and at an adequate distance to the object measured. This perpendicularity is very important. Why? This way we can measure its real dimension, so bear this in mind when measuring. Ensuring that the real outer diameter is measured. This is also the measurement of the outer diameter. For the inner diameter, we'll use this pointy part at the top. You can slide this open like this. When measuring the dimension of a certain position, you need to slightly rotate the object. If you're worried that the measurement will slip up when you are rotating the object, you turn the lock screw clockwise to tighten it, and then measure the reading on a scale. These are the measurement methods for inner and outer diameters. The third way of measurement is to measure its depth using the endpoint. We can insert this into the object we want to measure and then push down the caliper. You will obtain a scale reading. Let's see how to interpret this scale. I will screw this tight. Let's have a look. Let's take a look at this. Before checking this, first let me explain what the main scale is and what the secondary scale is. The main scale refers to this part. This is the main scale. This part below is the secondary scale. We will use the main scale and the secondary scale to analyze it. We will use the main scale and the secondary scale to obtain our measurement. Let's take a look at this. Let's take a look at this. What's the point of the secondary scale is fixed in place. The value on the main scale that is closest to the left of the 0 line will be its whole number. The point closest to its right now is 15. So we've confirmed the whole number part. The whole number is 15. For the decimal part, we will check on the right of the secondary scale's 0 line. The line on the secondary scale that is aligned perfectly with the main scale will be the decimal point. And multiply that value by 0.1 for the decimal part. Let's have a look. I think that it is the number 1. Why? You can take a look at the 0.5 section. The scale is a bit to the right, but at 1.5 is to the left. So at 1, it looks like it's almost aligned with the main scale. So its decimal value is 1. Then multiplied by 0.1, which equals to 0.1, so its decimal value is 0.1. Add these two numbers up, and the reading will be 15.1. This is how the reading is done. Let's move on to the next practice. We will place the motor frame here. When placing this, remember that it needs to be perpendicular and slightly move it so that an adequate distance is obtained. Then we can tighten the screw to lock it. Next, let me teach you how to read this measurement. According to the methodology discussed before, first we need to find the 0 value point of our secondary scale. We will mark the scaling on the main scale that is closest to the left of the 0 point. What is the closest value? It's 22. Our whole number is 22. Next, let's take a look at the decimal part. For the decimal part, we check on the right side of the secondary scale's 0 value point and look for the lines of the main and secondary scales aligned together. Let's have a look. It's around 4 over here. We can check again, see if 3.5 and 4.5 are aligned with the main scale. If your measurement is also 4 like me, then the reading is mostly 0.4. Adding the 22 from before, it equals 22.4. This is the caliper's reading. Now that you've learned how to interpret the caliper's reading, we can move on to the next part and start with our measurements. After measuring this motor frame, we will fit each measurement into this 3-view drawing. You must practice how to use the caliper, because later, when we are making some parts, the 3D model for certain parts that can be found online won't be a problem, but sometimes it's hard to find some parts with the exact dimension, so you have to reverse engineer it and draw it yourself. Therefore, you need to learn how to do the basic measurements. Next, let's take a look at this 3-view drawing. Later, we will draw this motor frame. I will guide you step by step during this practice. Let's open the Solid Edge program on the desktop. After it's open, what we need to do first is to open a new drawing. We have an isometric part here. Once inside, what we need to do first is to draw the dimensions of the motor frame's front view. When drawing the front view part, we will draw this from to top view perspective. Drawing from the top view, we can place it at this location. Once we've determined this position for our drawing, let's take a look at this part. Let's recall a bit. This motor friend is symmetrical. This is very common in engineering drawings. So later we are drawing this in solid edge. You need to remember this. We should make good use of it. Symmetry to speed up our drawing. Why am I saying it like this? Let's take a look. Let's draw. In this sketching tool area over here, we'll click on this. We used line drawing in our last exercise. Our motor friend is rectangular. We can click on this inverted triangle. There are a few ways to sketch this rectangle. The first one is to create a rectangle by its center. The second one is to use 2 points to create a rectangle. And the third one is to create a rectangle using 3 points. The most commonly used method is the rectangle by its center. After selecting it, when we're going to enter the sketching area, do you remember the first thing we need to do? Correct. We need to lock onto the plane on which we're about to draw on. Since we're drawing using the top view, we usually place it at the XY plane. Press F3. After pressing F3, you can see that a padlock appears on the right, which means we are locked on. We have performed the locking action. Next, we are going to draw it. We are starting the drawing from the center. Let me show you first. I will show you a demonstration first. When we select the center point and drag it, it will be symmetrical. When we are drawing this, as I said to you earlier, our motor friend is symmetrical. But for a symmetrical object, we need an origin point of symmetry. My habit is to use the center of the coordinate axis, as the center of the object is to do symmetry. It is symmetrical as seen. From the y-axis and x-axis, based on this, we can easily perform the mirroring action. I'll show you how to do it. Let's draw. There's a reversed out section for width. We can fill in the value, or we can also check the command bar, which also has numbers. I will select the command to do it again. Create a rectangle by its center. If there are some dimensions that are already known, I can also type it here. For example, the width we want to draw is 15. We will press enter, and for the next entry, we can click here. The height is 22.4, press enter. The angle is 0 degrees, press enter. The width and height of this rectangle that we have drawn are already locked. So if you already know the dimensions, you can also draw it directly. This is one way to draw this. Practice a little bit. This is a drawing method of setting the width and height directly from the command bar. Next, we're going to show another approach, because we're currently learning the basic knowledge of sketching. So we're going to let you know of all possible approaches. You can try it out. The operation of these commands. The second method is this. I don't input the values at the command bar. I can draw this first. And then input its dimensions. Let's select this figure and delete it. Let's draw it again. Again, we choose to create a rectangle by its center. The hint bar will tell us to select the first point, so we will choose the center of coordinate axis. When we drag the figure, you can see that the dimensions are changing. So you can use the keyboard to input 15 for the next dimension. You can press the tab key to jump to the next dimension for input. Next is 22.4. Press the tab key again. The angle is also 0 degrees. Press enter. For the second method, you can input the dimension values directly. Some of you may ask, if you can draw it roughly first, and then mark the dimensions later, of course you can. Why? Even after we finish drawing, we still use the Smart Dimension tool. Why? We need to check if the dimensions we entered are correct. If they are not, there will be problems afterwards. So let's move on to the third one. I will undo this. Again, I will create a rectangle by center, select this, and then drag it out an adequate size. We'll drag to 15, and then to 22.4. After getting a closed dimension, then we use the Smart Dimension tool to mark the dimensions. We can set this to 15 and press enter, then the width to 22.4 and press enter. These are the 3 ways we can draw this. You can practice and try using these 3 methods. After we finish drawing the contour, we will begin drawing the inner contour. You can see that the horizontal distance to the inner contour is 1.6. Let's first omit the circular patterns. Let's ignore them for now. Let's see the distance of the inner contour. The distance is about 4. Well, the distance over here is 1.6. Let's see how to draw this part. We know the thickness to the inner contour. Now we're going to use another drawing method. There are other ways to draw it, but we want to show the features of this command. That's why we're using the following method. We'll use this offset command, which means that I will select a line and design the distance from it. That's why it's called offset. Let's click on offset and select the line we want to offset. You can take a look at the hint bar which says to click on the element you want to offset. So I will click on it. After selecting it, the distance you want to offset will appear on the command bar. The distance we want is 1.6. Let's draw the line with the smaller dimension first, then press enter. Next, just move the cursor without pressing any other keys. When you move it to the outside, it will offset to the outside. When you move the cursor inside, it will offset to the inside. Let's offset inwards and press enter. You can practice drawing using the offset command. Once you're finished drawing, we still have lines at the top and bottom at a distance of 4 mm. Next, we will draw the line segments. At this moment, we can move the cursor to this position, and you'll notice that a symbol appears. That symbol means that my cursor is in touch with this line. So now I can left click and drag out the line. You will probably ask, then right click to cancel the action, which means that you're finished with the line segment. Once you've finished drawing the line segment, you may say that there is a dimension between these 2 lines, and it was not defined. We can always finish drawing the line first, and then mark the dimension between this line and this line. Then adjust the dimension and press enter. This line is finished. You can practice this offset function. Once this line is drawn, we need to draw the same line below. For this, we don't need to draw it. Why? Because we have the dimension set at the beginning of our drawing. I told you to draw this on the coordinate axis, so we have this x-axis that can be used for symmetry. Next, we'll select this function called mirror. This mirror function must be used on objects that are symmetrical for a better effect. Let's first click on the mirror function. When selected, check on the hint bar. It says to select the element to modify, which is this one. If you want to select more than one element, you can press Shift or Control. We'll click on this line segment. After that, notice that a dotted line will appear. Since we're using the x-axis for symmetry, we will drag the dotted line over here. We'll click the cursor on the x-axis and press enter. This axis of symmetry is now drawn. You can press Escape to cancel, and this command will end. What name should we give this file? Let's name it MotorFriend. We'll click on the application icon and click on Save. When saving the file, where should you save it? You need to pay attention and remember the destination of your save file. Let's save it at the desktop. We'll create a folder at the desktop because later we'll be placing all the files in this folder. Remember that. If you're going to draw this for a long time, since this course is going to take a while, you should develop the habit of placing the folder in a fixed destination. Whether it's the computer at school or your own computer, D drive is the most convenient so you can save it there. For the name, type in your class ID for an easier identification. When you leave, you can save the file into your cloud drive. Next time before class, place the file on the desktop. I will type in my class ID, 11901. Afterwards, I will put all the files in here, click it to open, and here we will type motor friend. Let's save the file. During the design process, you must save the files, because we are using a 3D software which consumes a lot of power. During your operation, if there is an error or the computer has more computational loading, the computer may crash. Therefore, you must develop a habit to save the file every time you achieve a certain progress to ensure that during the whole process, there will be no mishaps. When we're done, we're going to extrude this. The process we just did was all in 2D. Bear in mind that the figure needs to be reversed out. Let me show you the case with an error. If I erase this light segment, notice that it will turn white when it is white. It means that this figure is not closed. It cannot be so. We have this function. If you encounter an error during the drawing process, it is quite troublesome, so I'm showing you an example with a mistake for you to see. Let's zoom in. When I'm dragging this line over here, I don't connect it. You notice that there's a gap. So it is not completely closed. Later when I'm extruding this, I won't be able to do so. At the relate group, there's a connect lines command. It can connect them. After selecting the command, check the hint bar that says to click on the key point, which is this part. That needs to connect to the outer part. This line will be extended so we can use this method so that when the line is very close, it can connect them together automatically. Once this is connected, the color of the drawing will be reversed out, which means that it is a closed surface. It must be a closed surface in order to be extruded. If it's not, then you can examine it, and then use this method to fill in the missing gaps. Let's move on. Let's go back to the 3-view drawing. We've already finished drawing this. We can see from the top view drawing that the thickness of this part is 4.9. Let's go back here. We're going to extrude a 4.9 thickness to face straight towards it. We can press Ctrl plus H, then we'll use the select tool and select this part, which we want to extrude. I tend to tilt this a bit to the side. When selecting this, you can do it on the inside or the outside. Because I click it on the outside, the close contour on the inside will do nothing. I can extrude this. The command bar will appear over here. There are some options on the bar. We can click this to check it. The first one is if you want a definite value or beginning and end. The next one is whether you want symmetry on both sides or not. We won't be doing both sides symmetrical. This next one will affect our selection. There are 3 options, which includes excluding the inner contour or using the inner contour only. Here we will choose excluding the inner contour. This Solid Edge software is quite smart. It will guess your intention. If it guesses wrong, we can change it. In principle, if it doesn't guess it wrong, then we don't need to do this part. We can pull the arrow to extrude. We will drag this out in this direction. A dimension will appear. At this time, we will type in the value. Let's type 4.9 and press enter. Notice that the software guessed wrong. So we'll undo this and select it again. This is wrong. What should it be? It should include the inner contour, extrude this. This is now correct. We're typing 4.9 and press enter. For options in the command bar, only modify them if you have special needs. If not, Solid Edge sketching is quite accurate. The rate of mistake is quite low. Let's move on. After drawing up to this part, let's go back to the 3-view drawing and see what to draw next. This front view drawing is almost done. You can see from the front view that there are 2 sets of dotted lines. What do these dotted lines refer to? They refer to these holes. Next, we need to draw these holes. Pay special attention. There are only holes on the top and not on the bottom. These holes were later be used to fix the frame onto a board. Let's move on. So let's move on. Next, we're going to draw the holes on this surface. First, we'll select the circle command. After selection, we'll go to this surface. When we move onto this surface, a padlock icon will appear, which means to lock onto the surface plane, press F3. When it's done, we will press Ctrl plus H, and I will look straight at it. This way is more convenient. Next, notice that this plane is aligned to this light's center point. So you can select the center point and drag it, and you will notice that a dotted line will appear. At this time, we don't need to align the other center point to draw it directly. We can drag to draw the circle. The dimension for the circle was R1.4, which means that its diameter is 2.8, so we can drag the circle unit, a dimension that's close to 2.8, and then press Enter. We'll leave the rest for a Smart Dimension tool to do. We need to confirm the dimension anyway. What's its distance to the edge? It was 3.5. Press Enter. After it's done, mark the dimensions. What was the dimension? Radius 1.4, so the diameter is 2.8. Input 2.8 and press Enter. When it's done, click on the Select tool. What do we do next? We need to make the circle symmetrical. Onto the other side, we'll press Ctrl plus H to view towards it, and select the Mirror command. You can check the hint bar. It will tell you to select the element to be modified, which is this one. Where is the axis of symmetry? We use the coordinate axis to draw this. So you can use the z-axis. You can also use the object center point to draw it. I will choose the z-axis. Click on it. The symmetrical circles are now drawn. You can double check. If the dimensions are correct, the distance is 8. A red symbol will appear here, which means that these two circles are symmetrical. Once it's done, we'll click on the Select tool and drag these two through. Use the dragging method to get this effect. The motor frame is now finished. You can practice making this. When you're finished, remember to save the file. After saving, let's have a review. When we are doing 3D modeling, the procedure is very similar. We begin with the sketching tools. These ones over here, which are on the line. The rectangle, the circle, there are some circular arcs as well. We'll teach you how to use it, if given the opportunity. Next, we have the offset and the mirror, these dimensions. For the light segments are marked, and after completing a closed surface, use extrusion or removal to complete the shape that we want. Next is the Smart Dimension. Remember to save this file. We're saving this as a motor frame part file. This is it for today's lesson. Next, we're going to use another method to draw a solid using solid edge. Our practice example will be the wheels that we will be using. Let's take a look at the following drawing method. We can close the motor frame file. Because we've already saved it, let's start from the beginning. We select New and choose the isometric part. Next, we'll draw a 3D sketch. First, practice a bit and draw this. When sketching this drawing, I will first draw it for you to see. I will also explain to you a few frequent problems that you may encounter, so that when you're drawing 2D sketches in the future, you can use the following methods that I will teach you now to correct them. First, let's open the Solid Edge program. Let's go into the Solid Edge program. Let's select New and then choose the isometric part to go into this screen. When we are sketching, we'll select the Light tool, and we usually select the top view. For drawing, let's click on top to view it. When you move the cursor over, a padlock icon will appear. Press F3 and the padlock will appear on the right. To lock onto this plan, you need to pay attention to this, although this action is very basic, but it's also very important. Next, we'll first draw a light segment which is 19. When drawing this line, We can type in the length directly. Correction, it's not 19, it's 18.5, press enter. When it's done, left click the mouse to confirm this direction, then move to the side. This length is 5. Remember to keep this perpendicular. This is 1. Press enter. Then left click the mouse. The next segment is 19. Press enter. Let's make a mistake on purpose. I will draw the line a bit sloped. I did not keep it perpendicular. Right click with the mouse to cancel the command. How do we correct this? There are correction commands in the Relate tools. Regarding some line requirements, you can check this part later if you are interested. Let's take a look at this function. That keeps the line horizontal or vertical. There will be a description on it. It makes a straight line, or 2 points horizontal or vertical. If I click on this line, it will be horizontal. Next, let's mark the dimensions. Let's see if what we drew was correct. 18.5 is correct. This segment is wrong, so it needs to be changed to 5. This segment is 11. Press enter. Next is the segment. This one is also wrong. We'll change it to 19. The next part, during the sketching process, we will continue to finish the remaining dimensions. We'll select the line command. We'll select this point. We can drag this to an approximation and correct it later. Later we will still use Smart Dimension to mark the dimensions, so we can roughly draw out these lines. There's an action that I want to explain to you to avoid problems when sketching this later. For example, when we're drawing this line, let's draw it again. When dragging this downwards, you will notice that it will be related to the line aside. In this case, do not let the dotted lines appear, because when we are drawing this, these two lines are actually not related. It is not related to any of these lines. Know that if the dotted line is established, it means they are related. It will take time if you need to delete this. You need to check the original drawing and check if there's any relationship between these two lines. If there's not, we do not let this relationship be established. Next, we'll finish drawing this. Once this is closed, the inside will be colored. Next, we'll mark the dimensions. Here I will leave a mistake so that later I can teach you how to correct this. This segment should be 18.5. Now it has this additional segment, right? We'll delete this and use Smart Dimension to correct this. It will be this segment with this other segment. Be careful to select the correct lines. Drag this out, zoom out. Remember to use the zooming function for detailed adjustments. I'll change this to 18.5, press enter. One by one, we'll fill in all the dimensions. This is 6.5, press enter. This is 2.5. During the drawing process, if you just started and you're new to this, you may encounter some dimensions that cannot be modified. Since this drawing is quite simple, I suggest that you draw it again, it will be faster. When you become more and more proficient and you're familiarized with the functions, you can make the corrections instead. Otherwise, if you make too many corrections in the beginning, you end up wasting a lot of time for learning. And I worry that you will get confused. Therefore, if there's a problem during the drawing process, just start over again, it'll be faster. Once you are familiar with the software, we'll then move on to the practice more advanced function. I need to mark this last dimension. This is 1.5. What do we do next? We'll save the file. When saving the file, as mentioned before, we need to form the habit of saving the type of files in the same folder. It will take us a couple of weeks to finish teaching the drawing part. This is a wheel. The wheel has the black rubber tires and the ring, which is the white portion of the wheel. Let's change the name. to white. Wheel rim, and press save. Once this is finished, you may think this is strange. Where are we supposed to draw the circle? How can we extrude a circle? You've asked the right question. The action we're going to do this is another tool for solids. This one is extrude. Now we'll be using revolve. We can use the revolve function to complete our following action. Let's click on revolve. After clicking on it, you'll see this. After we click on revolve, this command bar will appear. The command bar will have some simple options that we're going to do. This is a surface which we will revolve. So we'll choose face. So that when we move the cursor over, it will select this face. We're going to revolve 360 degrees. So we don't choose a definite value, just 360 degrees. Next, we'll select this. We only change this option, and the rest can remain the same. We'll select this. After selecting the face, press Enter to confirm, or you can right-click your mouse. Next, we need to select the line of edge to use as revolving axis. We'll use this line at the center. Click on it and it will revolve to create the shape of a wheel. You can practice this part. When we revolve to create this, it cannot be recognized to have the shape of a wheel. The next thing that we'll do is to remove the sections that are hollow. Let's take a look at this. We need to make an elliptical hole here. The length of the ellipsis metric axis is 5, and the length of the mirror axis is 2. The distance of its center's location from the wheel's center is 15. Let's do this part next. First, let's go to this plan. We'll first select the sketching tool that we want to use. We will click on the inverted triangle next to a circle and choose Drawing and Ellipse by its center. Click on it. A command bar will appear. Let's click on here and fill in the values based on what we just saw. Press Tab to jump to the next dimension and type in 2.5 for the mirror axis and press Enter. The angle is also 0. When it's done, we will lock onto the plan. When locking the plan, you need to pay attention. The plan we are locking on is this one, between the two circles. They're in different planes. They have a level difference. So you need to pay attention to this part. The plan we're referring to is this one. We'll select it and press F3. Once it's selected, we'll press Ctrl+H, and we can view towards it. This is the center. We will let the solid edge program understand our intention. We want to align to the center and move upwards, more or less around this place. We will later use Smart Dimension. To mark the dimension, we will left-click with the mouse on this location. After that, we'll use Smart Dimension to mark the dimensions. When marking this, select the center and this location. Let's get close to the ellipse so that it can know our intention. Then mark the center of the ellipse and drag to the side. This action will be a bit hard to perform. You can practice a couple of times. Then input the dimension to be 15. Afterwards, we'll click on the Select tool. What do we do next? We need to make this hole. After that, we want to distribute this evenly around here. We want to do this array and make this 1, 2, 3, 4, 5. A total of 8 holes evenly distributed. We'll use the array function. Let's move on. The array function is here. First, we select our object. The entity we want to array is this. When we selected this plane, the array was not selectable. You need to select the 3-dimensional hole that we want to array. Then we click here. You will see the way of filling. We will choose the circular method to array. After that, select the plane. We first need to select the entity that we want to array. Then select the circular array. After that, you will ask you to select the surface you want to process, which will be this surface in the middle. So you need to confirm that the surface you selected is correct. Press F3. Per next step, the array will have a center point. When we're locking onto the center point of the array, on the control bar there will be an option to select a center point. Otherwise, it may lock onto something else, since the default setting is center point and end point. However, we want to select a center point, so we need to confirm that first. After that, we can move over. We need to select the center point of the array. When a cross symbol appears, it means that it's locked onto center point. We'll press enter. When it's done, you'll have an array number and you need to input the amount of copies you want. Our number is 8, we press enter. After enter, the entity will be evenly distributed on the wheel surface and display an array of 8 holes. You can practice this part. When you're finished practicing, remember to save the file. Let's move on. Next, we'll drill a spindle hole for a TT motor. The size of the spindle hole is about 5.8 in diameter. This spindle hole is not completely circular. It has 2 line segments. We measure this with the caliper, and in measure 4, we'll use this parameter to drill a spindle hole. Let's close the PBT file first, and then let's take a look at this. Let's turn over the side. We'll drill it on this axle. We'll first select the circle from center tool. Let's first lock onto this plane. Later on, each time we need to change planes, we need to lock onto the new plane. Press F3 to cancel the lock-on. Then select the new plane, and press F3 again. Then press Ctrl plus H to fast towards it, and select the center point. A lollipop or match shaped icon will appear. Drag this out. The diameter for this is 5.8. We can type it in directly. When it's finished, we will draw a rectangle by center. We will drag this rectangle out here. The width doesn't matter because we will process the width in a simple way. So we will type in 6. The height is what's important because the distance of the 2 lines is 4. So we will input 4 and press enter to confirm. Once this is finished, we can remove the lines that we don't want. Let's check if what we drew is correct. This is 5.8 and this is 4. They are both correct. This is what we want. We can use this trim tool to remove the lines that we don't want. We don't want this. We keep the lines that we want. The distance between this line and this line is 4. The circular hole diameter is 5.8. When this is done, what do we do next? We need to cut out this hole by the depth. When the contour is drawn, we will perform its extrusion. The length is 15 mm approximately, or 1.5 cm. Let's drag this downwards, then input 15, and press enter. The depth has been confirmed. The drawing of this white part of the wheel is finished. Let's save this file. Next, we're going to draw rubber tire, which is the black part. How do we draw this black part? We'll first draw this 2D sketch, and then use Revolve to create it. Let's do a demonstration. Let's create a new file. Click on Create. Then select isometric part. Let's select the top view, like this. And we're going to draw the sketch. First, we'll begin drawing from the center of coordinates and drag the distance. This is 26.5, press enter. We'll draw the first segment, which is horizontal. Then we drag this upwards. This is 15, press enter. Left click. Then move horizontally, typing 11 and press enter. Then we move down. Let's first tell the software our intention. We'll close this gap. We draw this part first. Then draw the arc. When drawing the arc, the distance is only 1 and intersects with these 2 points. Let's take a look at how we will draw this. We need to draw an auxiliary line here. We will erase it later. Let's click here and input 1 mm, press enter. Left click and then drag this downwards, press enter. This line that we just drawn can be deleted later. We'll draw an arc using 3 points. This is the first point. This is the second point. And this is the third point. And we will draw the shape. Then we'll erase the line segments that we don't need. This is not complete. Next, we'll use Revolve to create the entity. Click on the Select tool and then select Revolve. At the command bar, check if it is set to face. And the rotation is 360 degrees. We'll do according to what is set on the hint bar. We'll select our face and right-click the mouse or press enter to confirm. The axis of rotation will be the y-axis. Click on it and it will create this by revolving. Next, we'll save this file. Let's name it Black Rubber Tire. And press save. Let's give it some color. Since it's a white ring and a black tire, let's add some color. So I will teach you how to do it. After drawing these two parts separately, these are parts, and I will teach you how to assemble them together. After assembling them, we will then proceed with the coloring. Let's go over here and select Create and then choose Isometric Assembly. You can choose to include the current models. We'll use if given the chance. We'll choose this isometric assembly. In this isometric assembly file, we will begin assembling the parts. Let me introduce you to the interface, which is slightly different from before. Why? Because the main purpose here is not for drawing. This is to assemble all the parts together. So here you can see assemble and commands related to assembly. We also have move and drag. You can see that the ribbons here are different from the ones in the other interface, because this interface is not for drawing. Let's go back to the assembly file. We're going to import the parts. The first thing to do is to insert component. Remember the destination of our folder. We placed it at the desktop, so we'll click on Desktop. Then select the 11901 folder and drag in the white ring that and the black rubber that we drew. These two parts are now inserted. How do we assemble this? When you drag the parts in, notice that assembly commands will be colored. Let's select Assemble. When doing this, we need to establish their relationship. There are several of them and I will explain to you about some of the commonly used relationships. We move the cursor over this command and animation will be displayed. Mate align is to match two faces together. Align is to align two features on a plane. The third one is to align this axis with the other axis. After selecting these two axes, they will be aligned. We'll use these three commands for our basic learning. Since they're both circular, it means that they both have their corresponding axis. We'll click on the Align Axis command. We'll first select this object. The point we want to move it to. We want to move this over here. We'll select this. This is a circle, so it will naturally choose its axis. These two parts will stick together. You will notice that they are not in the same plane. What should we do? We'll establish the next relationship. There are two options. The first one is planar align, and the second one is mate align. In this situation, using mate align doesn't make much sense. We need to choose align plane. which plan, list plan, needs to be aligned to list plan. The assembly is now complete. There is a flick command here. The flick command is to reverse the direction of the assembly. You can reverse the assembly. Since this assembly is what we wanted, we don't need to perform this action. Practice doing this part. I will save this file. When saving, we can give it a name. My habit is that if this assembly is complete, the construction of the assembly is finalized, I will name this wheel, and then add the word assembly at the back. Because this wheel is completed and doesn't have any more components, and it's already complete, so I will press save. Making this up to this point, you can practice a bit. Once you are finished practicing, let's move on. I told you earlier that we will add some color to the wheel, because we talked about white rain and black tire, so we will add colors to them. Let's click on this style panel, and colors will appear for you to choose. First of all, it is a white rain, so we will choose a white for it. There are several white colors, and we will choose the normal one. It has several options, and we will choose the white color. You can also try out the different tones of white. After choosing the color, drag it to the white area. We want to color the white ring. When it is highlighted, it means it's selecting the black tire. I want to select the inner part. I will drag it inside and then let go. Click anywhere on the side, and you'll see that the ring is now white. We'll click on the style panel again. I need black tires, so I will select the black color. There's a black color over here. Drag it in, and place it at the black tire. And let go. This black tire is now finished. After applying colors, the model looks more similar to the actual object. We'll save the file. We can practice this part. After learning the basic 2D and 3D drawing, I will be teaching you the next segment. When we are using many parts, we don't actually need to draw each one of these parts. Why? Because we won't use more of our time in the mechanism design part. After knowing the basic drawing functions, we will spend more time in the simulation and thinking of our assembly and mechanism. In reality, many of these parts' CAD files are available for download in many websites. From my competition experience, some of the parts used for competition have their CAD files uploaded. In our course, these two parts that we did during our practice are quite simple, and that it will not take much time to draw them. You can apply some basic functions and use them for learning. But for other parts such as the motor, the control board, or the sensor, drawing them will require more time. For these parts, I do not recommend that you draw them by yourself. I recommend that you search it on website and download them. Later, I will teach you how to search for them, which websites have this information. After finding these files, we will download them. What are the things we need to pay attention to when we are planning on using these files? Let's take a look at these two websites. These two are the websites I recommend using. Of course, there are other websites, but I usually go to these two. The first one is GrabCAD. Let's take a look at it. The first website is GrabCAD. Actually, there are a lot of files related to robotics. Check the images on the background. It's quite abundant. Let's perform a search. We'll perform basic operations. For you to see, click here and type in TT Motor. MOTOR. Forgot to delete this. The search results will be displayed here. There are many motors that we can use. Let's choose a few to have a look. Such as this one, we're clicking. And we'll give you a demonstration on how to assemble this. The most important part is this, loading. 3D viewer, we're clicking. In this mode, we can perform more actions on it. Here we can view the 3D model. It usually has cross sections. We can take a look at X cross section and see the internal structure. We can even generate an exploded view. Let's cancel the cross section view. We don't need this. Here we can perform an exploded view. The more you drag the bar, the clearer the exploded view. And you can see how this functions look like when it's exploded. This is the internal structure of the TT motor. It will look like this. If you're interested in its dimensions, you can click on Measure to measure the dimensions. If this is the motor that you want, what do you do next? You can download it. When you enter, you can create your own account by clicking on the Create Account. I have already created one, so I will sign in directly. After logging, we can download the file. There's a download button here. After downloading, let's have a look. The key point was to teach you how to perform this. We'll click on Show in Folder. We will extract the file. And confirm the file was in a download folder. So I will extract directly. Once the file is extracted, let's click into the folder to see there are a few files inside. Commonly, we are given a step file, or even a solid edge file is possible. Most are step files. In order to avoid errors between softwares, when using different file formats, we can open this state file. The files used in each software cannot be opened in different softwares. We will open the solid edge program. We'll click on Open, and then Browse. The file was extracted to the download folder. We will search based on the date, which is today. Open it. At the file format option, I need to change it to all file types. We choose the state file and press Open. When opening the file, it will ask you the template and the file type you want to open. For a TT motor, we can guess that it is an assembly. Since it has many parts assembled onto it, it cannot be a part. It should be an ASM, assembly file. We will click on Confirm. When importing this file, it needs to rearrange the file. Let's wait for it. The file is now imported. What's over here are the different part files. When this is done, what we need to do next is to save this as a different file, because if we are going to use it in solid edge, we tend to use solid edge file format, so we need to save this file. We will save the file. Where should we save this? We'll go to the desktop and open this 11901 folder. We'll create a new folder. This is our TT motor, so we'll type in TT motor. Open the folder and save the file. When it's done, we can take a look at this folder in the desktop. TT motor. The file is here. However, notice that the other part files are not here. See? These part files were actually not saved in here. If you have an assembly file, you also have part files, but they were not saved in here. I'm here to tell you that this is incorrect. If you want to save the file, sometimes during the saving process, the password get interference. Therefore, I don't recommend that you click on Save File. We will pack it instead. We'll go to Share and select Package to Save all the files used to another file format. Let's pack this. See, these are the files that will be packed. They were not copied before, so there was some interference. We can choose whether to keep the structure of the folder or copy them into the same folder. We will choose to copy all files into the same folder. Where do we copy this? To here. Save to folder. Click on Browse. We will change the destination. We'll go to the desktop. After that, we'll select the 11901 file. Inside the 11901 file, we will create a new folder. We will name it TT. In order to differentiate from the other folders, I will type TT and now repeat motor. We will type in TT and press confirm. We'll save the file here and press confirm. Then we'll press save. It's complete. You can have a look. Let's go back and check. Inside the 11901 folder, the TT motor was created using the package method. You can see that there are many files. Check the TT motor folder. We use the save file function. So this one has problems. So you need to pay attention when doing this. When saving the file, the original part file will not be copied over. If we want to ensure the file is complete, we should use package instead, and then save it. This way will be more complete. Next, let's take a look at this. Let's click on this motor. Let's practice again. During the earlier practice, in order to let you know the difference between these two saving methods, so I show you both methods. The second method is the correct one. The first method may omit some files. There's another operation step. If we want to do it correctly, there's another way. Let's take a look at this. Let's find another file that we didn't download before. After downloading, I'll show you again. We'll extract the file and press confirm. Once the file is extracted, we'll open this folder. Once inside this folder, we'll find a state file. Let's go back to Solid Edge. Let's choose all this file from before. Click on the application icon and click on Browse. We'll click on Downloads. It's this mini brushed motor. This is the zip file. I choose the wrong. I shouldn't have chosen the zip file. We'll open the extracted folder. Select the state file and open it. When opening it, it should open as an assembly file. This part is done. We'll first save the file. When saving, we don't use the save function. We're going to package this directly. Otherwise, the files might not be complete. We'll use package. It will ask if I want to save the modifications. I will press yes. It will first convert the file once. What is this action actually doing? It's converting the original file format into Solid Edge's file format. This must be performed. After this file is converted, this is actually not what we want. What we want is the package file. We will select the folder that we extracted and press save. This next step is what we really want. We will select Save to Folder. We will click on Browse. Then go to Desktop and then select the 11901 folder, which is my own folder. I will create a new folder. I can decide the name of this folder because it is a motor, so I will type in motor. Then we will add a mini, which means miniature. Press confirm. Inside my folder, there's a folder named mini motor. Press confirm. All files will be copied into the same folder. The most important thing is to ensure that all the part files will be copied. The action is very important. Sometimes when you save a file, you forget to do this action, you'll only get an assembly file. The part file did not get copied alone. Let's press save. Let's check the mini motor folder. Inside the 11901 folder, I will save all the files here. This action is very important. You can practice this part a bit. After introducing GrabCAD, the next website is Instructable. There's a lot that can be used in here as well. Let's do keyword search. We'll use the word robot for keyword search. Once loaded, here you see that there are a lot of words. You can have a look at them. For the process of making a robot, when your experience is yet abundant, you need to refer to the works made by experts. Many people upload their works onto these two websites. If you're interested, you can also upload your creations. You can go and check them yourselves. For example, their spider robot was created by a very well-known person in Taiwan. If you are interested, you can reproduce this. You can click into Browse. Many people upload their project creations. You can check them out if you're interested. The parts that we will be using for our course were downloaded from the GrabCAD website. We can only use them for educational purposes and must not use these files for commercial purposes. This is our moral obligation, and you will also need to attribute the creators. Let's move on. For the conversion of the file into the file formats of different softwares, these are some common drawing formats. You can have a look to know a bit about it, so that next time you're doing file conversion, you will know what it's for. However, if we want to use these files, all must go through a file conversion into a solid edge file in order to be used. Next, let's have a review. When we download a CAD file from a website, we need to save it as a solid edge file. When saving, we need to pack all the files and save them into the same folder. Otherwise, what will happen is that only the assembly file will be copied out without the part files. This problem will continue to happen in the future when we're doing the assembly. Let's move on to the next unit, which is the parts assembly in solid edge. Before we begin, allow me to tell off about a concept. This concept is the issue of folder management. To be correct, as the number of files increases, it is actually not good to place all files in the same folder. So we'll do a simple classification. How do we make the classification? This is a very important point. My suggestion is this. For example, the motor and motor frame can be put together in one folder. The controller board, the controller and the battery goes together if the application or the space where they are located are closed. We can include them in the same group. Why do we do this? First, it's easier to find. Second, it forms this habit. Because later on, if you want to draw the design of a larger sized robot, there may be groups of students drawing this together. During the drawing process, for example, one student is in charge of the wheels, the motor, and the chassis. After drawing, when you need to do the assembly with another student, this student is in charge of drawing the mechanism, such as the gripping or lifting mechanism. If we need to pack all the folders and copy them over and over, it may cause confusion, so we will separate them. The first student is in charge of everything related to the chassis. The student with the gripper will be responsible for that. Whenever he needs to copy the files over, he only needs to copy the section that he is in charge of, so he will not touch part for the chassis. While the student in charge of the chassis will touch the gripping and lifting mechanism of the other student. From their making process to the final moment of assembly, as long as each one brings out their own part, and the assembly conditions still meet, then assembly will be fine. When doing this, the classification of the files will be based on their functionality or their physical condition and put together. This way, one of the folders will be given to one student to do or manage. When assembly final needs to be performed, then we pull them all together. Our files will be divided into list groups. The main assembly will be separated into secondary assemblies. The secondary assemblies will be examples that we just did. The chassis is a secondary assembly. The lifting mechanism is the second secondary assembly. When packing the files, the student in charge of the second secondary assembly will copy those files. When it's time for the main assembly, each person in charge of each secondary assembly will bring the files over, and then one student will be in charge of the assembly, which is a more convenient method of management. Later during the making process, we'll follow this mode so that you know how we will be operating this. Next, when we're doing the assembly in solid edge, after bringing out all the parts, we'll be using a function called an add in place. Why? For example, we bring out several motors and then combine them together. Here is when we use the add in place function. I will create a new structural component to assemble together the motor and the controller. I will give you a demonstration. This is a website. For parts that are commonly used, you need to download all the files. We will copy this website, paste it here, and press enter. We will go into a folder. You can pack the whole folder and download it. Let's have a look. Click on download to download all the files. It will take some time to download. Do we leave this site? If we leave, the file will not download. You'll begin to download this file. After it's downloaded, we'll click on Show in Folder. We will extract all the files. Click on Extract. Let's click on the extracted folder. We will copy all these files. We'll go to this folder and copy this. After that, we'll go to the desktop and link to our folder. We can use it when we need it. We will delete these files that we use for practice to avoid errors from occurring. They were for practice anyway. Keep this folder the same as mine, so that it's easier to follow. Let's delete these files. You can practice this part. Let me show you first the final look of the 3D model of our vehicle used in our course, so that you have a clearer understanding for the making process later on. We're going to make a vehicle like this. During the making process of this car, how do we stack this up one by one? I will explain this to you. For example, when we are displaying this, we may need to make some parts disappear. Unclick the box and the part will disappear. If we want to do a simulation, how do we, let's say, drag, click here, and then press confirm? We can then make these parts move up and down, and so on. We'll go over each one of them to see how to do this. We'll go step by step and tell you how to do this. First, let's hide all the parts that we don't need at the moment so that it looks cleaner. And you know what we'll be doing next. This is how the thing that we need to make looks like. I will hide the parts that are not needed. We don't need this. We'll first make a simple housing, which we will call moving platform. For the things that we will need later, we will bring out the key part. For example, we'll hide this. We'll also hide the copper pillars. The copper pillars are inside the moving platform, so we need to hide this. This part still remain. We just remove them from view so that it's easier to operate. What we need to do next, we'll lift these parts and this bull-eye omni wheel. How do we proceed? All these parts are already made and downloaded from GrabCAD. The wheels were drawn by us. What we will be doing next is on the chassis. It is like a building block. After bringing out some of the necessary parts, we will use the edit in place function to create a new part and place it in. For this hose, we'll use a projection method to make the hose. What we need to do first is to assemble these parts such as the motor and wheels into the same space and arrange them. When their relative position is done, then we proceed with the edit in place function and create a new part. Let me demonstrate how to do this. First, we'll create a new assembly. We go to create and select assembly. After choosing assembly, let's think about what we need to do first. We have the motors, the wheels, and the motor frame. We need to bring out these three parts. Let's go to our original folder and create a folder named the motor related parts and place the parts here. First, we'll insert all the parts that we need. Select Insert Component, then select our folder. The files are in the motor main assembly folder. The first thing to do is to bring out the TT motor. After that, let's see how we're going to place this. What is the position we want to place this motor? If we want it to be positioned like this, you can place it like this. Once it's done, let's have a look. Let's place everything unanimously. This is the top view and this is the right view. Later, when you're operating, we will unanimously place them at the right view so that it's easier for everyone to operate. Let's have a look. This is the location of our wiring connection. So we will place this on the inner side. What we'll do first is to import the motor frame. Click on Insert Component, then go back to the previous level, drag in the motor frame. For the operation, we should have screws. But in order to simplify the work, we won't be talking about screws in this course. But remember that the location for our screws need to be included as well. Let's assemble. For screws, this is circular, so we will use the Align Axis command. Notice that there are holes at the bottom of the motor frame. We want these holes to face downwards because we want to fix this onto the board below. So you need to pay attention to the direction of the holes. 2 key points. First, the motor wires should face inwards. So we need to place the motor frame on the inner side. Also, the holes of the motor frame must face downwards. These conditions need to be fulfilled. If you make a mistake and then need to correct it, it's not hard to do, but it will take some time to do it. We align to axis. Then this hole needs to align to this hole. After that, this hole below needs to align this part of the motor. When it's done, these two faces need to align. Should we align edges or faces? Of course, it's align the faces. We'll select this face. And then this face to align. The motor frame part is finished. Next, we need to assemble the wheel. Again, select Insert Component, and then import the wheel. If we're dragging the wheel, we don't need to do that with the ring and tire because they're already part of the assembly, so we'll drag this file in. Again, we're aligned to axis. Select the object to move and then select the location to be moved. Next, we need to pay attention to this part. When the wheel is assembled onto the motor, it is pushed against this section of the motor. For a section, we'll use Mat Align selectless face, and then move over to selectless face. Then assembly is completed. The assembly of the motor is more or less like this. Let's save this file. You can try this out. Once the assembly of the motor is done, let's move on. Next, we'll take a look at our vehicle. The motor portion of the vehicle is complete. We need to set and assemble them. We also need a bull-eye Omni wheel. We will first assemble these two motors into a new assembly. What we need to do now is to create a new assembly. We'll select an isometric assembly. After that, we'll select Insert Component. What we're going to insert is our motor assembly. Let's drag this in. Once dragged in, the right view is facing upwards. Next, since these two motors need to be aligned, we can select all of it by dragging it like this, or you can do it in another way, which is this: press Escape to cancel. We'll select it again. We'll select this component on the side. The motor assembly, when you select it, the whole assembly will be selected. When you select this, notice that component code 3D Gumball will appear. What does this mean? After you select it and the 3D Gumball appears, I can move this object according to the different axial directions. It has the X, Y, and Z directions. Let's go back to the right view and look at it from the top. We'll select this axis, and then drag the object to the side. We'll later use it for its symmetrical properties. We'll place it at an approximate location. What's the next step? Looking from the right view, we'll use Mirror to place the other motor on the right side. What we can do is this. At the array group, select the Mirror Component command. This is already in 3D, so its component to be mirrored. Select the component to be mirrored. Select this. And click on the tick to confirm. After that, it will expel the reference plane to mirror. Since it's in 3D, we need to move this. We're going to use the XY plane. Click on it. And the object will be mirrored on both sides. We press confirm. It will expel the mirror result. We just need to press confirm. Once it's done, we'll go back here and have a look. The results will look like this. Press finish. The two objects are now mirrored. Let's check. This is correct because it's mirrored, so the wires are facing inwards and the motor frame holes are facing down. It's more or less like this. You can practice this part. What will we do next? Next, we need to draw the chassis. At the moment, it's just a draft, so we can roughly draw the shape and then make the detail modifications. So what do we do now? It is something very important. Select Let This Code Assembly. What we need to do next is create a part in place. You must pay attention to this part. After you select the command, it will ask you if you want to save the file. You need to save in order to continue. So press yes. This is a part that we're going to create next. In this folder, we should go up one level. Since it is a chassis, it's part of the moving platform assembly. So we'll name it chassis. Let's name it chassis and press save. This will ask you where the component should be placed. We can designate a new location, or not designate anything. We will place it according to our location of assembly and modify it if needed. After confirming, the first thing it asks you is what type of unit standard this component uses. We'll keep using the isometric part and then click on Glatique. We have an upper chassis and a lower chassis. This one will be a lower chassis, so we'll native lower chassis. And then press save. You can try this out first. We'll continue with the next step. After that, you'll notice that everything is white colored when you're drawing this chassis. Check what's shown on top. It says synchronized part. This used to be an assembly. Now it is a synchronized part. Now we can begin with our drawing. Notice that the mode is different. It looks like the interfere for parts instead of assembly. We can now begin with our drawing. We will be drawing the symmetrical part. So we'll first draw a rectangle back center to make a simple chassis. If we need to make it more complex, we'll come back to it later. First, we lock onto the plane. Then click on the center and drag out. The detailed parts will be adjusted later. We'll align it approximately to the wheels. We will make it like this. It's okay if it's a bit bigger. After that, the next step is to arrange the light segments. Let's first extrude the thickness. We select it first. Since most of the materials used for laser cutting are about 3 mm, so we'll extrude 3 mm. We input 3 and press enter. Let's take a look at this. Placed in 3 days. Next, we want it to be installed under the motor, so we're going to move it. However, we cannot move it in this mode. Why? Because it is at the drawing stage, it is a synchronized part, so it cannot be moved. What do we need to do in order to move it? Let's click on the X. We need to switch to assembly mode to move it. You need to pay attention to what's shown at the top of the software. It will hint to you whether it is at assembly mode or synchronized part mode. Click on it, and the 3D gun will appear. We'll drag it downwards. After that, we can match them together. We'll use this. Then we need to do something, which is to extrude the holes. Let's assemble this first. Let's select Make Align and then this face to be aligned with this outer face. Once finished, it should look like this. We will perform detail adjustments next, because there's interference with the wheels. Let's go back. And we're going to arrange this. How we're going to modify this drawing, when you click on it, the option of Edit in Place will appear. You can also right-click the mouse button and select Edit. These two are the same, so we'll click here. Let's have a look. We're going to make detail adjustments on this light segments. We don't care about the dimensions for now. The advantage of this is that it has Lego blocks. You find the key parts, and then use all the Lego blocks to combine them. We won't be using building blocks here. We'll be using board made by 3D printing or laser cutting to combine with these structural parts. We first find the key parts and then draw the structural parts to assemble them. At this stage, we don't consider their dimensions. Yet, we will make fine adjustments later. At this stage, we will focus on its overall appearance. Next, let's take a look at this part. We will assemble and arrange this. Let's select line. We first need to lock down the plane. Because this is symmetrical, we can draw half of it and then mirror the outer side. We want to draw it up to the front arc of the wheel. We first move the cursor to the center point and move upwards to let it know what you intend to do. That you need to align with the center. Let's zoom in on this part, because we don't want to touch the wheel, but we want to align to the motor. So we will drag this up to this location. We avoid the wheel and drag up to here, then move down. Press Shift and then scroll wheel to move up to the drawing. We will align at this location. In the beginning, we already touched the center point. so it will predict that you want to align to this point again. This segment is finished. Right-click the mouse to end this command. Once this part is finished, what do we do next? Next, we can use the mirror command. On these line segments, these lines are not joined, so you press and hold the Shift key and select these line segments. When selecting, make sure you select the lines instead of the endpoints. We'll mirror the Z-axis and then press confirm. The chassis is now finished. Press enter again. Right-click the mouse to finish. And click on the select tool. This is now finished. We don't need this part. What do? We'll click on the section and drag this back to remove it. The overall look of our chassis is complete. You can practice this part. When it's done, we need to bore holes. There are 2 holes at the bottom part of the motor frame. How do we pierce these holes onto the lower chassis? There's a very important function called project. This function can project the holes. Which plane do we want to project them on? You need to select it first. You need to select the plane first. The upper plane is stacked behind and it's not easy to look at, so we'll choose this plane at the button and press F3. When it's done, it will ask about details of the projection. We don't need to do anything here, so we just click on confirm. Next, we can go here to have a look. At this time, you may not be able to see it very well. See, there are holes over here, but it's not easy for you to see. At this time, I suggest that you do this. We'll go back to assembly mode and slightly drag the object down so that it is easier to see the holes. But when you drag the object, there will be conflict with the assembly conditions. The software will wonder, were you supposed to align them? Why not anymore? Since we are going to do this, if we can modify this condition, we do it. If not, we would just remove them. Let's delete this. Once this is done, let's continue. We need to project the contour of the holes. At this moment, we're at assembly mode, so we cannot edit this. We need to select Edit in place and switch to this mode. Check that it says Synchronize Part at the top. Let's go back to this last step to project to sketch. We'll select this plane and press F3. After that, it will ask you to confirm, so you press confirm. Next, select this hole. Notice that it will be projected onto a sketching plane. Project these 4 holes. You need to pay attention when selecting to see if what we are choosing is what you want. It's hard to select. Once the 4 holes are projected, we're going to extrude them next. We'll click on this and pierce through. We click on this one too and pierce through. Once it's done, we need to save the file. Always save after a few steps. When it's done, close this and reassemble it back. Let's go to assembly mode to have a look. Our chassis doesn't have any assembly conditions, so again, let's do the axis alignment first. Although when we drew this using projection, but there's no condition established, so we will need to complete this action. How many conditions do we need to establish? Technically speaking, we should give condition to all 4 holes. We can also choose to adjust them when a problem arises. In principle, all holes should be given an assembly condition. Once it's done, we'll mate align the faces. Once it's done, we'll click on the Select tool. We're finished with the assembly conditions. Next, we need to bring in the Bullseye Omni Wheel. Let's go back to our folder. Let's go to desktop and to the 11901 folder. The Bullseye Omni Wheel is located in the Other Types folder. Inside the Public Files folder, we'll copy this. And go back to this folder. The Omni Wheel is assembled onto the chassis. So we can place it in the mirror related folder, since they are all assembled together. We'll place it in the motor related folder, since they are all together, and probably won't be separated. Next, I'll bring in the Omni Wheel. I select Insert Component. And then Bullseye Wheel, we drag this in. Next, we need to assemble the Omni Wheel. We can do this like building blocks, placing them approximately. This will align to this plan. Let's assemble this. We first do the planar alignment. And establish their relationship first. We select Mate Align and align to this place. When this is aligned, let's go to the right view and select the object. Then drag the object down and then to the side. You'll think that it is tilted. On this 3D Gumbo, you click on any part on this circle and drag it to rotate the object. However, the angle of rotation is not accurate yet. We just rotate it approximately. When we really need to be precise, we still need to mark the dimensions. We know that this Bullseye Wheel will be placed at this location. We'll first bore holes so that it can align to the axis. We need to select Edit to edit this object in place. We'll first bore a hole. Let's press F3 first. Pay attention to this. It needs to align to the center axis. So you can choose the center point or the midpoint of this light segment and slightly move upwards. We'll draw a hole of an approximate size and adjust its dimensions later. Let's draw an approximation first. Later, when need to make adjustments, we can then make more precise modifications. We pierce through. We can move this over. Let's close this. Synchronize part mode and go back to assembly mode. We'll click on Assemble and then select Align Axis. This axis needs to align with this axis. It seems that it's not enough. What should we do? Let me teach you an amazing method. This has exceeded boundaries. We'll click on the Select tool. And again select the Edit in Place option in this mode. We can actually drag this directly. An arrow will appear and you can drag this. This is actually the same extruding action. Next, we need to bore these two holes so that the Bullseye can align to them. Let's close the chassis. Synchronize part mode and measure the dimensions of the Bullseye Wheel. Let's close this. Then go to the button to have a look. We'll select Edit on the Bullseye Wheel. Let's measure its dimensions. We'll use Smart Dimension to measure the distance between these two holes. What is the distance between the two holes? It's 38.8. So the distance from the center to the hole is 19.4. Let's close this and go back to here. The distance from this hole to this other one is 19.4, so we'll select this and edit it. Let's go to right view to look at it and select the circle command. We'll first move to the circle center. We need to lock onto the plane first. Then at this plane, we need to tell it that I need to align with this axis, then draw a circle. We'll adjust its dimensions later. The distance from the center to this hole is 19.4, press enter. Then input the diameter of this hole, which is 4. After that, we'll use the mirror command to mirror it to the other side. We'll select the object to mirror, and then the mirror axis. Now you can understand why it is important to place the center point at the coordinate axis. It is more convenient for mirroring, and you don't need to keep making adjustments. Then use the select tool on list holes to pierce them. When this is done, we will align the bull's-eye wheel to the axis of the holes. Let's align them. We cannot do this when it's at a synchronized part mode, so remember to close it and go back. We can only do this at the assembly mode. You will be switching between these two modes. Let's click on Assemble, and then Axial Align. Bull-eye wheel to chassis. It doesn't allow the movement. Why? Let's check the assembly conditions of the bull-eye wheel. These are assembly conditions. The first one is made aligned to lower chassis, and the second one is aligned to the holes. What does this mean? This means that there is a conflict with one of these assembly conditions, so we can remove the condition. This is most likely to cause problems. One is to mate align, and the other one is to axial align. The axial align condition is more related to our current condition, so I will delete this first. After deleting this, we will align this to these two holes, and we won't align the part in the middle. We'll select Assemble, Align, and then select this hole, then this second hole on the side of the bull-eye is aligned with the hole on the chassis. This is complete. Next, after the Omni wheel is assembled, we need to check if the bottom part of these two wheels are aligned. During our earlier design, the height of the bull-eye wheel was quite uneven. Some were taller and some others shorter. Having this been made in bulk, there's some error margin. Therefore, during our design, we will design them into two ways. The first one is to let you can place it on top or below the board. In this case, we need to make the hole in the middle bigger. Let's first measure the dimensions of this bull-eye wheel. We can also use what we did earlier was to go into edit mode and measure the bull-eye wheel in its individual state. In reality, we can use this PMI to measure these dimensions while still being in assembly mode. We'll click on Smart Dimension. When measuring, pay attention to this. The part we're going to measure is at button, so pay attention to where you're measuring. This measures 29, so of course we click on the 29. Later we will input 29. To pierce the hole in the middle, this is 29. We'll click on the Select tool, then right-click the mouse to choose Edit. We'll adjust the size of the hole. We'll delete one of this. Since we may accidentally tap on when operating, we should not have two dimensions showing, because the software cannot know which one to follow. It's 29, so we'll input 29 and press Enter. We'll lock this number. This is finished. We'll close this and return. The reason for leaving out this hole is that if in any case we end up buying some bull-eye wheels on the which are taller and some are shorter, if the one bought is shorter, we can assemble it from below. If it is taller, we can assemble it from the top. Depending on the situation each time we buy this, we can adjust accordingly. The operation of the chassis is finished. You can later practice this part and see if there are any problems. The operation of the chassis is basically complete. For the making of the chassis, some students will use the laser cutting machine. In this case, there won't be any issues. The dimensions are precise. But if we are going to make them by hand, it's not possible to make the dimension to the decimal point. This will be quite hard on the people who are in charge of making the parts, so we're going to slightly the numbers so that the dimensions are at least whole numbers or with a decimal of 0.5. If you mark 0.3, I believe that no students can achieve such precision. Let's go back. We'll select this object to add it in place. When we are working with this, the parts nearby can cause interference, we have a method which is to hide all these mirrored parts so that it is easier to look at. We'll remove these parts, such as the mirrored motor as well as the original motor assembly, leaving only the chassis. Later when we need them, we can right-click the mouse and select Show All. Let's take a look at this. We'll readjust the dimensions. Select Smart Dimension. We'll change this 62.44. This number is too complicated. Here we can take a look at this. The arrow will determine the direction you want to modify, whether it is left or right. However, since in the beginning we drew this symmetrically, so the direction of the arrow will cancel out with the symmetry of our drawing. So even though I made adjustments, it won't be able to adjust to a certain direction. But for other conditions, it may not be so. The direction of the arrow will influence the direction of its modification. In our situation here, since our design is symmetrical, so it will be make the adjustments symmetrically. If later on we encounter this situation, I will explain more. We'll first mark each of these dimensions. Let's change the width to 63, and then press Enter. Let's move on to the next dimension. What we need to adjust next is the distance between the holes of this motor frame. We'll adjust them to a whole number to 19, and adjust this symmetrically. When this is done, the next dimension is this, the distance between this hole and edge. We'll adjust it to 52. For this case, the arrow will make a difference. When adjusting this part, we can adjust for one side to move in closer or to move out further. In this case, I want this distance to be smaller, so we'll shorten this. This red arrow over here will be moved closer. Let me show you. When I confirm this, the top will come down. See, it lowers down. The direction of the arrow will determine the situation of its adjustment. Let's continue. Next is this segment. Let's change this to 75. Let's change it to a whole number. The part to be adjusted is this one, so this line will move up. Let's change this to 75. Let's see how it adjusts. It goes up. Let's adjust this part. We don't need this to be so long since there's a lot of space on top. The arrow will move upwards and not downwards. Moving it downwards will have different results. We'll change it to 30 and then press Enter. In this case, the hole gets cut. So I need to adjust this hole first. It should have a certain distance with the edge. Let's see how much distance is required. Let's first mark the distance between the hole and the edge. We'll click on the hole, then on the edge, and drag this to the side. Let's shorten this and change it to 17. I want to adjust the lower end. We'll set the distance between these two to be 17. And notice that we need to lock this dimension so that the circle and the edge will maintain a distance of 13. The padlock icon must be activated, then press Enter. We can continue with the adjustments of this part. Notice that when I adjust the distance of this hole, these two screw holes on the side will move alone because these two holes were designed to be on the same level as this hole. Next, we'll adjust this distance. Let's assign a whole number. We'll change it to 30. Notice that when I change this to 30, the holes in the middle will also move up. Confirm and it will move up. So we need to pay attention to this when designing. Once this is done, let's move on. When designing the chassis, the edges are sharp and it's not good. We can add some fillets. In Solid Tools, so we can use this fillet option. When creating the fillet, we need to select this corner line. It will ask you to input the fillet radius, so we will set it to 2. When the first fillet is set, the following fillets will have the same value of 2, so you don't need to adjust the dimension. We'll set all the fillets to 2 and add the fillets one by one to each corner in order. Other than looking better, when the machine gets bumped, the corners don't get so damaged. If it is a right angle, it gets easier to get a corner chipped off. When it's done, this part is completed, and we can close this. Next, we can call back all the parts, so we'll click on Show All. This part is now finished. The chassis of our vehicle will look like this. We can move on towards the next part, which is the making of the upper chassis. Next, we can draw the copper pillars. Before we begin, let's see how we're going to draw the copper pillars. Let's have a look. Let's select one and check it. We're going to add it on in place. We're going to measure its dimensions. The main dimensions is the distance between these edges, which is 4.99. When drawing, we directly set the distance from edge to edge to 5 mm, a whole number. We'll go back to the chassis and save the file first. After saving, let's draw the copper pillar. Let's create a new file. In this case, we don't need to add it in place, although it can be used, drawing in this mode. It's usually because we want to establish a relationship with assembly. When we place them together and operate it, it is much more convenient. However, if it has something to do with the original assembly, when we work on it independently, the loading on the computer will not be so heavy. Later, when we are drawing, as the amount of parts on assembly increases, it consumes a lot of resources. If the computer doesn't have an independent graphics card, the computer will become very slow when running the program. We don't use add in place if there's no need to. We'll go to Create and select Isometric Part. We'll draw the copper pillar. To draw the copper pillar in a rectangle group, there's the option for creating a polygon by center. We'll select 6 faces like the copper pillar. We need to input the distance, which refers to the distance from the center to the edge. Our measurement was 5, so the distance from the center to the edge is 2.5. We press Enter. The angle remains 0. With this parameter set, we can create a polygon. We'll first lock onto this plane. Click on it. This is done. The first copper pillar that we need is 25 mm long, so we'll extrude to 25. We input 25 and press Enter. We need a copper pillar with female thread on both sides, so we'll carve out a hole in the middle. The size of the hole is 3 mm. Because we used M3 screws, so we'll choose a diameter of 3 mm. We do the same for the other side. We turn this over. We'll move over here and draw the circle at the center. After that, we didn't draw it, so we will draw it again. The diameter is 3 mm. Press Enter and come here. We can go over here to let it know about our intentions. We forgot to change the plane to lock on to, so it couldn't lock onto this plane, so we need to do this again. As you can see, the lock on plane feature is actually quite important. The mistake I made shouldn't have happened. We input the diameter. Again, we move this plane and lock onto it. Here we will let it know of our intentions of placing this at the center. It will figure out that this is what we want. Doing it like this, it should automatically lock on, see? A center point symbol appeared. It's done. You must align it at the center. You need to pay attention to this. If it's not at the center, there will be problems when assembling. We'll extrude inwards. Generally speaking, the holes on the copper pillars have a 10 mm depth. So we will extrude 10 mm inwards, then confirm the same with the other side. Extrude down 10 mm and press Enter. The copper pillar is now finished, and we'll save the file. We'll click on Save As. Since it's our first time save, pressing on Save and Save As is the same. We're going to save the file We'll first place it in this folder and name it copper pillar. We'll also show its length, so we'll name it copper pillar. Double female ends. Its length is 22 mm, then press save. Once this is finished, we'll go back to the chassis. We need to drill 4 holes on the chassis. Next, we'll place them onto the assembly. We'll go back to the chassis assembly, select Edit in place, and drill 4 holes on the lower chassis. The size of these 4 holes will be standard, which is 3 mm. We'll lock onto this plane and draw the circle around the location and later adjust it using Smart Dimension. The size is 3 mm, and then it's alright, we'll come back later for adjustments. After that, its diameter is 3 mm. The distance from the center to this edge will be set to 5 and press enter. This point to this edge, let's move this upwards. This is 6.5, press enter. His hole is complete. We'll also make a hole over here. Again, we'll drill a circular hole. Remember to lock onto the plane. When it's done, we will use the Smart Dimension to adjust it. The distance between the center and this edge should be 5, press enter. This dimension should be 3, press enter. Next is the distance between the center with this edge. Here you notice that if you want to modify this, we cannot do it because it's blue colored. It's driven, so it cannot be modified. There are 2 ways to solve this. First, we can lock this dimension, but it still cannot be changed. What does this mean? It means that somewhere over here, there's something that was not set right. Which part? It's this part. When we're not able to change this to a locked dimension, it means that there are conditions missing in one of these dimensions, or there's a design condition that is bound. In our case, it's probably because the data given is too little, so it cannot make any positioning. So any positioning will be meaningless. We must mark this dimension first. When you encounter a similar problem in the future, which dimension cannot be locked, you have to check if there's any parameter missing or if any other feature is locked down. Let's adjust this and change this to 15. Remember that the direction of the arrow will affect how it's modified. We'll change this to 15, then press enter. After changing this, the other side will also change alone. The top is already defined. We'll modify the dimension below. Remember to lock on. When this dimension is changed to 15, let's delete this first. After deleting it, we'll mark this dimension again. From this center to this edge, drag it down. Now this dimension can be modified. If you don't update the old dimension marking, you cannot adjust it. When the outer parameter is set, we need to delete the old dimension and make changes. This part can then be completed. When you're doing this, you have to pay attention to the order. Which dimension is priority? The dimensions marked later can only be driven, and they cannot be modified. You must have this concept clear. You will encounter this kind of problems very often when operating the list in the future. So when you encounter a problem, you need to know how to solve it. After these 2 holes are drilled, we need to mirror them next. Let's select this hole first. And then we'll use the axis of symmetry. Since the other side is the same, we can use this midpoint, click on it, and this is done. Next is the hole edit button. Use the select tool. Select mirror. Choose the part you want to mirror, then draw this line of symmetry. Both sides are finished. Since they are symmetrical, they share the same properties, so we don't need to make any more changes. Let's tilt an angle. Next, we'll use the select tool. Because we may end up choosing a dimension, if you're worried that you accidentally click on a dimension and it's bothersome to do so, you can disable all PMIs. to make it simpler. Let's save the file. This part is complete. We can close this and go back. Remember to save the file. Let's move on. We can go back to assembly. Here you can see that it says that there is a failed assembly relationship. We'll later go back and check which are these failed relationships. Let's go back all the hidden parts. Click on Show All and all parts will return. To see what failed assembly relationships there are, you can click on it. It will tell you if there are any problems. Click here and it will show the problems. The reason is probably because we adjusted the position of host, so the position is off. So let's take a look. Click on this and we can make modifications. Let's go back and check this. Click here. And you will see some failed assembly relationships. They are all related to merging conditions with the motor assembly. We can think about why it went off. That's because we modified the host of the motor friend, which caused our assembly relationship to be off. Initially, this distance was fixed, but then got moved, which caused this problem. In this case, for the sake of finding a simple solution to this, we will delete the mirror. Because the mirrored object will maintain a fixed distance, so we will remove it. Later, when this part is adjusted correctly, the mirror relationship will be solved easily. Notice that after you remove it, the lightning icon has disappeared. There are no longer failed assembly relationships. Next, we will mirror this again. Click on it. To select them all more conveniently, click here. Select the motor assembly from this list. We have the mirror command over here. After select the command, we need to select the object to mirror, which is what we've already selected. Then click on the tick. After that, we need to select the mirroring plane, which is this one, so we click on it. Here we just need to click on confirm. Then we press finish. You can see that there are no more assembly relationship problems because we modified the dimensions, which cause problems with the mirror components. Do we need to assemble this part? This is up to you. This was usually made using mirror, so it already has a relationship established with this component, so it's not necessary. If we encounter any other problems in the future, we will make further modifications. Let's save the file. Once the part of the chassis is done, we need to assemble the copper pillars. We'll add in the copper pillars. We'll click on Insert Component and go into our folder to bring in copper pillar 25 part. When extracting, we first align by axis. We'll select this hole. This face also needs to be aligned. We'll first select this face. Let's click on the Select tool again and select the Align command, select the face. Then select this surface. When it's done, press Enter. We can then move on to assembling the next copper pillar. We can use the Select tool to drag in the copper pillar like this. We can drag this directly. Instead of using the Insert Component option, as long as the part has been used before, we can drag it again from the side. Let's click on Assemble. Then align to axis. When it's done, next we'll align this face to this outer face. Then click on the Select tool, and then drag another rod out. We can drag two pillars out, which is more convenient. Click it and hold the left mouse button. Remember to first click on the Select tool. We have two rods now. Next, we select Assemble, then Axial Align. Then select this axis, then select Mate Align. This is done. Moving on to the next one. It's done. We'll save the file first. This part is complete. Next, we're going to make the upper chassis part. When making the upper chassis, we can actually reuse this button chassis. So this is a method that we can do. We can create a new part, select the isometric. Part, once it's opened, there's a command over here called part copy. For parts that are similar, we can use this method to design them. We'll select the lower chassis file, then click on open. When opening the file, it will ask about list conditions. We don't change anything, because list parts are usually similar. We just need to press confirm. If you want to change its size, you can do it here. If you want to make changes in the XYZ directions, untick the cup ratio option and adjust them one by one. Since what we need is 1:1, so we don't need to change anything. Press confirm. Once loaded in, remember to press finish. Why do we need to bring this in? Because some of these holes are not needed. We only need the 4 holes for copper pillars. We can remove these holes. Click on it and then press delete to remove the hole. We need to choose right to select the round entity. We'll remove all these holes. The top chassis is now complete. The top chassis should look like this. We'll adjust the other holes later on. So now we can click on Save As. Wait, we can actually click on Save, because it's the first time save, so we can just press Save. This will be named Upper Chassis, then press Save. After that, we can go to the chassis assembly and assemble it. Let's click on Insert Component and drag in the upper chassis. We'll assemble this part onto the assembly. We'll align to the axis. For the axis part, we need to be careful and select the right part. This is the first one. Then this one. Next, 2 points are aligned in a line. The next part is to align these 2 faces. This one to the other one. Then we're finished. Our chassis is complete. Let's save the file. We can move on to the next part. You can practice a bit. So far we've completed up to this step. Let's take a look at what we're going to do next. After the upper chassis is finished, we need to assemble the copper pillars. Our current pillars are 25 in length, and the ones on top are slightly longer. So we'll use the method from before. We'll use part copy to make the rod. Again, we create a new part and select the isometric part. After it's open, we select the part copy command. The part to be copied will be the copper pillar. Double female and I'll open it. We don't need to change anything from here, so we'll press confirm. Once it's done, we only need to modify its dimensions. It was originally 25. We will change it to 30, press enter. Once it's finished, we'll save the file as a new copper pillar name. The original name stays, but we'll change it to 30. Press enter. It's finished. Let's go back to the upper chassis. For the upper chassis, we need to make some holes. These holes need to be drilled. And then this hole over here is done. Let's take a look at this part. we'll go to the upper chassis. We're going to begin with the drilling of the holes. We first lock onto the plan, and then straighten its orientation, so that it's easier to work with. We'll press Ctrl+H to face towards it. Next, the hose. This hose should be the same as these other ones, should be drawn at a distance of 6.5 mm from the edge. We'll draw two holes first, which are also 3 mm in diameter. We move down and place it to an approximation. This is also 3 mm. When it's done, we will mark them with Smart Dimension, which is this point to this other point. This distance is about 30, then press Enter. Next is this edge to this hole. This is 75, press Enter. Next, we're going to use Mirror to deal with the other two holes. We select the Mirror command and click on this hole. Align to the Z-axis, click on the Select tool again. To mirror the next hole, select Mirror, click on the hole. Align the Z-axis. When it's done, we'll click on the Select tool. And we can drill these holes by means of extrusion. It's finished. We'll save the file. After saving, we'll go back to the chassis assembly. The holes will be generated there. Suppose your holes were not generated, you can go to the tool ribbon and select Update, Model in Use. If the part has been worked on separately, once you go back, you can use this option to update the file. After that, we'll go back to Home and select Insert Component to drag in the copper pillar. When it's done, we click on Assemble Axial Align. After aligning to axis, we need to mate align. This rod is a bit too low, so we need to move it up. We'll use the Select tool and click on the pillars. A 3D gumball will appear, then we can move this up. Then we can continue with the mate alignment, this face to this face. We'll drag another pillar. Click on the Select tool. Don't forget last step. Again, Assemble Axial Align. Click on this axis. Next, mate align to this face. Then use Select tool to drag another pillar. Next, assemble mate align. You can do mate align first. You can make modifications later if needed. The top and bottom holes are concentric, so it's alright. Click on this axis, and you will align it. Let's drag in another one, Select tool. Drag this, it didn't work. Let's drag it again, Axial Align, Assemble Axis. Select. We selected round for this. Let's go back and check. This is correct, but we clicked on the round line, so its position is turned 90 degrees, which is wrong. Let's delete this relationship and establish it again, Axial Align. Select this hole. This is the correct way. If any problems occur, we can delete the relationship and define it again. Then mate align, and this is finished. Let's save the file. I taught you before how to add colors. The copper pillars could be added a bronze color. We'll click on this style board and choose a bronze color. Let's choose brass. We'll drag this out. Because this, for our sim, we can apply to all models and not do it one by one. Click on apply on all models and all 4 pillars will be colored. We'll do the same for above pillars. So we're dragging the brass color to list pillars. Apply to all. And this coloring part is done. You can practice this part and finish this model. Let's save the file first. What we're going to do next are list parts at the top. We'll first organize those ready-made parts. The ready-made parts are in your folder. In the public files folder, there's a folder called ready-made components. We'll select a file named thread copper pillars, rod 5mm, and a motor driver, adapter board. We'll copy these 2 files, and then paste them at the top layer of our file. We'll organize them together in the public file folder. We also need other components, which are the Node MCU and the motor driver board. We'll copy them. Next, we'll go to the public file folder. There's an other folder. There's a battery holder here. We'll copy this and paste it here. This is probably enough. We have the copper pillars, the motor driver board, the Node MCU, and battery box. We can move on to the next step. We'll go to Solid Edge and create a whole new isometric assembly. First, we will bring in the files that we just organized. We'll go here and bring in the motor, driver, adapter board. After that, we'll go back and check the holes. Let's see how we'll assemble this. When assembling this, there will be 2 holes close to the top edge of the adapter board. Then it's this part. Then we have this 2 holes to the left. Let's take a look and check this part. The holes are closer to this edge. Then we have these 2 holes on the left, which is more or less what we just observed. When assembling, we have 2 holes at the top. Then we have 2 lower holes that are leaning to the left. We'll assemble it like this. For the next part, after determining the position, next, after it's finished, we'll insert component and bring in the motor driver board. We'll select this file. We can do a preview. There's a total of 2 assembly files. The first one is the connector, and the second one is the motor driver board that we want. We can drag this in. After dragging this in, the motor driver board is facing opposite to the direction of our assembly. We can adjust it, but it doesn't matter. We can turn it over during the assembly process. We'll select Assemble, then Axial Align. Then this hole will align to this hole. At this moment, you can see that it is reversed, so we need to turn it over. When it's done, right-click the mouse. After that, we select Assemble. Then Axial Align. Then select this hole. Then align it to this second hole in this adapter board. It's done. Right-click to finish this section. Next, we'll assemble the copper pillars. Let's click on Insert Component, then drag in the threaded copper pillars 5mm. Again, click on Assemble, then Axle Align, and align to this axis. Next, we need to pay attention to this. This should be reversed. The thread should face upwards. Next is this face. We need to align it to this face. Next, for a second one, click on the Select tool and drag the second pillar in. Assemble Axle Align to this axis. Then Mate Align. You need to press the mouse's middle button to rotate to the most suitable position. The assembly is complete. Next are the screws, which will be placed over the pillars. Here and here. Again, insert component, drag the copper pillar, assemble, over. And right-click the mouse. Then Mate Align. Once it's done, right-click the mouse. Then drag in another pillar. Click the Select tool, then Assemble Axle Align. Place it in layer. So we need to move this up a bit. We did not change this axis, so its assembly shouldn't be a problem. Assemble, Mate Align, select the bottom face of the copper pillar. Then select this. The assembly of the copper pillars is complete. Next, we need to assemble the motor driver board. We will Mate Align. Since we previously had two axes aligned, so we do not need any other constraints. We just need to align this face, and it will be placed on top of the copper pillars. Again, we'll select Insert Component. What's the next part? We'll bring in the Node MCU. We'll select the assembly file. We'll choose the ESP8266 file. Checking from the preview, it seems to be the correct file, so we can drag this in. Once dragged in, we can take a look at how we're assemble this. Our connectors should face downwards. Currently, this object is reversed. If you think that working with it is not easy, you can reverse it. We'll select this object, and after the 3D gumball appears, we'll rotate this 180 degrees. Input 1A0 and press Enter. This way it is better to work with and should be easier to operate. Once it's done, we'll move this closer to the board using a 3D gumball. After that, let's have a look. Next, we're going to assemble it. Let's have a look. In this case, we usually Mate Align first. First, notice that the antenna needs to face outwards, and the USB port should face towards this blue section. Let's Mate Align them. When you're trying to align them, you'll notice that you cannot select it. What is that? As the assembly contains more and more components during the assembly, it will not know which part to activate first. If all of them are activated, then it's quite troublesome, so we need to select this option. We just activate the part to assemble. We'll select which part we want to use for assembly. After that, we can select the part we want to assemble. We'll select this rod and assemble it. We'll select this pillar. This thread will be aligned with this wire groove for the DuPont line. When selecting, it should be aligned to this downward plane. The next step is also Mate Align. Let's move this. Press the Shift key to move it, and then enlarge. We want to align this face. We just align this face, and now we want this inner face. We select one less 90 degrees. Next, we come back here and align to this. It will position over. See that it's on top, so next we need to place it down. We'll also make align. The part to align are this black section to the group below this face. It's a bit hard to select. So we'll click on the Activate Component option and select this. We'll align this face to this other face. This is now fixed in place, see? Basically, we need 3 assembly conditions to complete it. Let's save the file. You can practice this part. We'll first save the file. When doing so, we need to give it a name. This is part of the controller core. So we can name this controller assembly. We'll first save it at the root folder and organize it later. Then we press save. Once it's done, we're going to place the battery box. Again, we'll insert component and go to our folder. Inside this folder, there should be a 1A650 battery. During our earlier process, we missed something at some point and it wasn't copied. It's okay. Let's go back to the public file folder and copy the 1A650 battery folder. Let's go back to this 11901 folder and paste it here. Let's go back here and again insert component. We are in the 11901 folder. Go into this folder and select the assembly file that we want. This one, we'll drag this in. After we drag it in, we're going to assemble it. You can see that it has a power switch over here, which should be at the rear part. Let's have a look. We're going to assemble the 1A650 battery. For convenience, we'll remove the cover. We'll select this cover part and hide it for a time being, or it will interfere with our work. Let's look at it from behind. Looking at it from this angle, we're going to do the simple assembly. Even though there are 4 holes in the battery box, but we did not leave that many holes. I'll explain later. Let's align the axis of this hole to this hole. Again, we need to activate the component. Then align axis, and it will turn over. Next, we move this down a bit. When moving this down, because 2 holes are aligned, this object is already assembled in place. Next, we'll make align. The face should be made align with this face. Let's check over here. The assembly for this uses 1, 2, 3 holes, not this one. Why not? There's a reason for that. Notice that there are many connector pins under this hole. Many components of the Node MCU are placed here. I don't want them to short circuit, so I will omit this hole. We'll only have a 3-point fixture and avoid this hole to prevent problems from happening. Then we bring back the cover. Our controller board assembly is like this. Let's save the file. After saving, we can close this. Why do we need to close it? Because we need to move our files. Let's go to the 11901 folder. We'll create a folder. This is a secondary assembly. What should this assembly be named? We'll name it controller assembly. And place all related parts in here. As long as it's used, I will place it in this folder. All lists were also used. I moved it wrong. Let's cut this and paste. it back. Let's drag in one by one the motor assembly. This one, then press Shift, drag it to the motor assembly. We have 2 folders. Next, we can assemble together the controller assembly and the chassis assembly. We'll create a new file. This third assembly we're making now will be the main assembly, because everything else will be assembled in here. So this should be the top level assembly. We'll select isometric assembly and bring in the components. First, we will bring in the chassis assembly. We're dragging the chassis. Next, we'll insert components and go up a level. Then select the controller assembly folder and drag in the controller assembly file. We'll use the method from earlier to assemble these 2 parts. The way we do this will be as follows. This part which a power switch can have the switch facing the vehicle's front or rear, depending on your personal needs, because what we'll do next is related to our mechanism. The practice using the mechanism will be set at the front of the car. So we'll place this switch facing the rear. Let's have a look. The switch is located here. We'll select this part. First, we need to activate it. Then this hole must be aligned to this axis, and see if it meets our needs. It's reversed, so we need to flip it over. Then right-click the mouse when it's done, because this will obstruct our view. So we can select this and move it upwards. Again, we click on Assemble, Axial Align. This hole needs to align to this axis. Then right-click the mouse to finish. This is correct. Next, we need to make a line. We'll select this first and then align it to this location. And it's finished. The vehicle's basic composition is like this. We'll gradually assemble the outer parts. Let's first save this. This file to be saved is the main assembly. On the highest level. Among all assemblies, this is at the top level, so we will save this at the root folder. We will name this assembly file Vehicle Assembly. Press Enter. Now that this is finished, after you finish practicing this part, we can move on to the next section. You can practice. Hello everyone, I'm Teacher Xie. The following unit that we're covering is a mechanisms design and simulation. We'll only be discussing 2 types of mechanism in this course. The first one is the lifting mechanism. For the lifting mechanism, we'll be using one as shown on screen, which is a 4-bar linkage mechanism. The reason for using a 4-bar linkage mechanism is that when we're performing the lifting action, the front bar and the rear bar will remain parallel. This way the cloud can stay parallel to the ground to perform the perpendicular gripping action. Let's simulation the movements. Select the drag component option. After analyzing these options, we'll use the default configuration. We'll select the part. This is our actuating bar, so we'll use this. We'll choose the free motion option, and we can move this up and down. When you're lifting this, you'll realize that the front and rear bars will remain parallel. This way we can allow our gripper to remain parallel to the ground. We'll be talking about how the process of this mechanism design will be performed. Let's give you a demonstration. We'll start with the vehicle assembly that we drew during our last lesson to perform the next step. First, let's go back to our folder and organize the servo that we are using. Let's go back to the desktop. Then go to our 11901 folder. Inside the public file folder, select the input-output module folder. They have provided 3 types of servos for you to use. For our lesson, we'll be using the MG90 servo. We'll copy this and paste it in the 11901 folder. For our mechanism part, we have a main assembly. Along with 2 secondary assemblies, we'll place the MG90 in a new secondary assembly folder and see it as the lifting mechanism. So we're naming the lifting mechanism, press enter. We'll place the MG90 into lifting mechanism. Let's go back to the chassis assembly. We'll insert our component. We'll move up a level. Select the lifting mechanism folder and drag in the MG90 servo. Run file should be this one. Let's drag this in. Once the servo is dragged in, let's place it at our expected position. After placing it, we'll draw down the remaining mechanism parts. First, let's have a look. This can be performed using the assemble command, so we'll click on assemble. Because we need to do planar alignment, we want this face and this other face can be aligned in the same plane. This alignment can be set to have a fixed distance, or you can keep it floating. We'll set it to fixed. Afterwards, when you're doing this, you can try it out. You can adjust this part for the alignment. You can have a fixed value or allow it to move freely. When set to floating, it means that these 2 surfaces are parallel. As for the dimension, it will be determined by the changing of our positioning. First, let's have a look. We'll set it to fixed. Then select this plane to align with this plane. In this situation, we need to activate component because there are too many parts, so we will activate component and select this plane. Then this plane on the servo will align with this plane. On the chassis, let's turn towards the front of the vehicle. We want the servo can be centered on the upper chassis. We're going to use another function of the assembly mode, which is this one, center plane. What is center plane? It is similar to Microsoft Word's centering function. This object will be positioned at the center of the upper chassis. You need to pay attention when using it. When the command bar appears, we need to select 2 planes. These 2 planes. We'll select this plane and this plane. They will align with this plane and this plane. When I click on this plane, it will be aligned. It moved. Let's go over here and see again. See, this plane and this other plane will align. This is the constraint of this servo. We'll click on the select tool to move it for you to see. It will be at a center position. This way, when we draw this, it will be balanced. After that, we can turn to its right side. Move this down a bit. We can adjust its position later. We are just doing a demonstration. You can also practice this part. The final design might not be like this, but during its design drafting, we can set an approximate location. Later, using the mechanism simulation, we'll simulate this to see if it meets our expectations. If possible, we can mark the dimension of the structural parts with more precision. Let's take a look at this. Now we can begin creating a part in place. Let's click on Create a Part in Place, and then press Confirm. Next, we need a lifting mechanism. So we'll name it lifting mechanism friend, because it's responsible for lifting action, and we'll add a friend. After that, you can first we'll begin our drawing. Let's first draw an approximation. Because it's a planar sketch, so we'll use 2 points to build a rectangle. It should be higher than this. Something like this. The bottom part should align with the chassis. Confirm. Next, we'll extrude a thickness. Since we're planning on making this using 3D printing, so we'll extrude a thickness of 2. It's about 2 for 3D printing. After that, this can be moved forward, so I will close this. We need to go back to the assembly mode. So you need to know which mode you're on. I will move this forward to the assembly position. Next, we're going to drill the holes needed so that this object can be installed at this location. Let's have a look. Let's go back here. Edit in place. We need to project all the lines for assembly. So we need to select this option to project to sketch. There are a few things to project. We first need to confirm the plane we are projecting onto. For more convenient operation, I suggest drawing it on this plane. You can also select this plane at the back, but your view will go obstructed by the servo. So I suggest placing it at the front. The operation will be easier. We're using projection anyway. Let's turn to this side and project these key features, such as this screw hole, this one as well. There's another screw hole here, projected. Next is the contour of the servo. Later we will gouge this out. For this part, let's have a look. There's a selection option over here. We can choose a single face, which refers to this face. Since the width is the same, so we'll use face projection on this plane. Now go back to the front. See? The contour has been projected on this plane. We'll click on the tick. Next, we're going to arrange the position of the holes. We'll enlarge this. When I remove this contour, I actually need this to be slightly larger because the dimension should not be too fit. So we need to do an offset. Let's zoom in. We don't need to offset by a lot. If it's too much, we won't have enough space to use. We'll change it to 1 mm. Once confirmed, we'll offset outward, but this offset is too big. 1 mm should be alright. Let's keep it at 1 mm and press enter. Next, we need to complete these holes in order to extrude them. This hole is about 2 mm in diameter. The same goes for the hole at the bottom. We need to complete it. Lock onto the center point, then draw the 2 mm hole. Next, we can drill this hole. The same for this one. We'll delete this original projected lines. You can delete 1 segment first, so that when it's time to extrude it, the whole contour will be extruded. Otherwise, it will extrude the area between the two contours. We'll remove the middle part. This part is done. Next, after we progress up to this point, I will close this and return for this frame. See if you want this servo to remain at a centered state, or lean towards the left or right. Because currently we're doing simulation. When we are certain to produce it, we can still make some changes. Let's cancel this center plane. Relationship first. Let's delete this. Assembly condition. Let's align this onto this friend that we just drew. We'll click on Assemble Axial Align. Align this axis with this axis. Then this second hole, align this axis with this axis. Next, this needs to pass through here, so we need to do Mat Align. Its backside will align to this plane. After fixing it in place, we can edit the friend. Let's move to its front view. We can hide the wheels. We can edit this edge. Let's switch to edit mode. Here, we can create a rectangle using 2 points. This is its edge. Lock onto the plane first. Then draw a rectangle. We will base the width on friend, which is 19.96. Then press tab to go to the next one. Change this to 2. We only give a thickness of 2. Press enter. We will extrude a thickness. Why do we need to extrude? Because we want to fix this onto this hole. Again, project to sketch and select this plane. Click on confirm. We need to project this hole onto this plane. Let's project it to the sketch again. Press F3. Press confirm. Select this hole. This one for the copper pillar. We need to project this to the plane. When it's done, press confirm. We can remove all these extra parts. Next, let's see, we don't need these. Because we used projection to find a precise location. So we can remove this. This hole needs to be pierced through. Next, we can make a simple assembly between these 2 parts. We need to close this. We'll switch back to assembly mode. Click on Assemble Axial Align. When it's done, we can make align. This plane should align with this plane. We have more or less completed the server frame. Let's move on to the next step. Let's go back here. We need to make a 4-bar linkage for the levity mechanism. We're going to make a bar. There will be 2 bars. To draw these 2 bars, we'll create a new file, select isometric, part. We'll draw a rectangle by its center. Lock on plane. Select center point and drag out. We'll set a length of 20 for simulation. We can adjust it later. 20 mm. The height of the board correction. We'll set the length to 30. It's a bit short. Let's set it to 50. Press enter. For the height, we'll set it to 10, so 50 by 10. We can modify this later. Press confirm. When it's done, we'll extrude a thickness. We'll give it a 3 mm thickness. Press enter. Next, we'll drill 2 holes. These 2 holes will be at the center line of our bar. So we'll lock onto the plane. From the midpoint of this line, we'll move a bit to the side and drill out a hole. Then select the Smart Dimension. Because we need to fix these screws, so we'll set them to 3 mm, press enter. We can fix the distance to the edge. See if you want it to be 5 or 10. We'll set it to 5, press enter. Because it's symmetrical on both sides. So we can use mirror. And mirror to the z-axis. Once it's done, we'll drill these holes using extrude. This one as well, extrude. If you want it to look nicer, we can make a fillet. Select this edge, we can set this to 5. Click on the wrong line, press Ctrl+Z to undo. Select fillet. It's finished. Remember to save this file. Where should we save this? In the lifting mechanism folder. Let's name it bar. This part is used for practice. We just want to do a simulation with it. Bar. We can move on to the next step. We also need to drill a hole here. This hole will connect with the bar. Let's go to Edit. We'll drill a hole. Let's first go to this center point. The hole needs to align with the center point. Our hole end, the center point should be on the same line. We can lock onto this point. To align, press F3 to lock onto a plane. Then drag this down. You can place the hole at any suitable location. Drag it, then input 3 mm and press enter. It's done. Let's extrude this hole. We drill out this hole. This edit is up to this point. We'll go back to the assembly mode for the next step. We'll click on Insert Component to bring in the bar we just drew. Let's assemble this first bar. This axis can align with this axis. The faces need to be made align. We'll select this and move it here. The first one is like this. I want the second one to be aligned with this plane. Right? I want these two to be aligned together. We'll drag in another bar. We'll click on the select tool and drag in the bar. Again, axial align. This axis should align with this axis. Next, we need to make a line aligned to this plane. We don't pay attention to the servo rotor for now. After that, we can measure the distance between these two. We'll be using these holes. In assembly mode, we'll use PNI to perform measurements. You'll see that the dimension is 44.35. We can use this dimension for the outer bar that we are going to make. We can also adjust the distance of this hole below. Let's give it a better number. 44.35 seems a bit strange, so we adjust it to 40. Let's adjust the dimension for this. We'll select Edit in place. Let's measure the distance of this hole to this edge. This is 15.37. We're going to move this up a distance of 4.35. Remember that the arrow. So our size should point upward. This is very important. If the direction of the arrow is wrong, then the direction of your modification will be different. This distance 15.37. We need to add a 4.35 adjustment. So it would become 19.72. Let's type in 19.72 and press enter. When it's done, We can close this and return. It's a bit off. This is probably due to an error margin in the dimension calculation. This is actually quite troublesome. It doesn't matter. We'll use this 39.99 dimension to make the outer bar. For the outer bar, we'll create a new part. We'll choose the isometric part. When we open the file, we're going to copy the bar from just now. Click on Apply, then Confirm. We won't modify it. We're only going to the dimension from here. Let's check list to holes, use Smart Dimension. Measure distance between the two holes. What we want is 39.99. So this is not good. We want it to be exactly 39.99. And evenly on both sides, press Enter. This will be a new bar, and we will save the file. We'll navigate bar 2 and press Confirm. When this is done, we'll come back to this Vehicle Assembly. Then go back to the main ribbon, insert component and drag in the bar 2 file. After that, we're going to assemble it. Axial align when it's done. We need to mate align the faces. At this moment, we'll align to one bar first. For example, align this face to this outer face. At this time, we can have a look. You'll notice that something is wrong. There's a gap here. This should be moved backwards. To be more appropriate, we can still adjust this. This is the main reason why we need to use CAD software. In general, when drawn by hand, it is on a two-dimensional plane. Also, when dimensions are taken into account, you need to calculate them. However, if you are doing simulation using a 3D software, you're doing the simulation in a 3D space. And the dimensions will be accurate. So when we're doing simulation, we can recognize if our assembly has any problems more easily. We need to delete some of the assembly conditions from this. We need to delete the mate alignment condition. This one here. We'll delete this. Next, the position of the hole is the same, so we don't change it. For assembly condition, we'll move this face to this surface. This is still not enough. Of course, we can think about a solution later on, with more adjustment options. But at this moment, because our assembly can perform our simulation, we'll perform a simulation next. Let's go back here. Next, we'll simulate this part. Up to this progress, we'll save the file first. After saving it, let's move on. For the simulation of the mechanism, we'll use the drag component command. There are some options over here, such as fixing the component's position. Basically, we'll use the default setting. If we want to learn more advanced configurations, we can adjust this one by one. We'll explain more in upcoming lessons. We'll confirm this first. After that, this is the first thing we do. There are 3 modes which are node analysis, detect collisions, and physical motion. If in the beginning, you use detect collisions option, it will be more challenging for our execution, because it has to execute many things. In the beginning, when we are not sure about what we are going to do yet, we don't need to do physics analysis. We'll select node analysis first, and check if the motion can meet our expectation. Next, we need to select the bar that we want to move. We'll choose this one. There are 3 dragging options, which are linear, axial, and free motion. We mostly use free motion, which is more convenient. We'll drag this bar, and move this up and down. See, I can know whether this bar linkage meets my expectation. We'll rotate this. You can try this out. See if there are any questions up to this point. Let's practice a bit. After practice, some of you may think this is too high. We want this to be lower. We can modify our bar. Simultaneously, for this motion simulation that we just did, We'll reset or undo it to go back to its original state. We can change the length of our bar. Let's modify the length of this bar. We'll select this bar using the select tool, then click on Edit in Place. We'll adjust the bar's length. We can use Smart Dimension to mark the distance between here and here. It's 40, right? We can change this evenly on both sides, and we'll change it to 60. Then press Enter. After changing this to 60, press Confirm. Let's go back to the vehicle's assembly. You'll notice that it's messed up. It's alright. We can go to Tools to update the model. Our assembly relationship is still there. It will not disappear. It was just a bit off. You just need to go to Tools to update the model and it will be normal again. Let's go back to the main ribbon. Let's simulate this again. Select Drag Component. Then press Confirm. We'll use the Node Analysis option to do this. We'll select this object and move this in free motion. We can see if its length can meet our expectation. It's close to what we are looking for. We can move towards the next step. We'll restore this back to its original state. The next step is to do collision detection. Here we'll be checking the motor's upper and lower limits. We'll select the object. Move this up and down in free motion. Setting. When there is a collision, a color will appear, see? When there's a collision, it will tell you that you're stuck. This is a detect collision function. You can also choose the next option, which is a physical motion. The physical motion option will consume even more resources. It's still alright when there are not that many components yet, but it won't be when there are many. We'll select the object and move this up and down. When it reaches this point, it won't move any further. Why? Because it's stuck here. Based on real physics, this won't go through. So physical motion analysis is the most accurate. In the beginning, you first finish making the motions that you need. When switching to physical motion, you will follow the principles of physics. If there's an object, it will get stuck. In this mode, we can simulate the design of the mechanism to fulfill our expectations. We have already defined list dimensions so that it's more convenient to make more detailed arrangements. Let's explain up to this point. You can practice operating these different simulation options. After you finish practicing, this part was to show what the steps are to designing the mechanism. Let's have a brief review. To make this overall view look nice, let's call back all hidden objects. We'll click on the Select tool and then select Show All. Now this looks more normal. The first thing we need to do is to bring in the actuator. We'll fix it in place in an approximate position. Next, we need to figure out how to fix the original mechanism with the new part. That will be in charge of the motion, so we'll create a part to fix them together. We call this a structural part. In mechanics, there are two categories, the movable ones called mechanism, and a fixed one called structure. This belongs to the structural category. The next mechanism is a bar linkage. These bar linkages can move, each one of them fulfilling a role, such as how high or how far to lift. This is what these mechanism components are in charge of. When using Solid Edge to do this, we first design the type of motion of this mechanism. Then, when we are dragging the components, we can measure the actual dimensions that we will need. After these two things are finished, we can then produce the components that we're actually going to use. This action here is done during the draft practice phase. We'll first define these dimensions, and when we need to use them in the next phase, we'll make them more specific. Let's explain up to this point. After the simulation of the mechanism part is done, we need to draw each structural component. Previously, we used laser cutting for our practice, so we used 2D sketching and produced them on sheet materials. For the next part, we'll focus more on the case that we're going to produce them using 3D printing. How are we going to draw the structural components? With special shapes. First, let's have a look. I will teach you how to draw this part that's assembled at the front. Let's see how we draw this. First, let's practice. We'll create a new file. We will create an assembly. Why do we choose an assembly file? Because later we will need to add in a MG90 servo motor. Let's bring in the MG90 motor first. Why? Because we need to combine the part with this MG90 servo, so the servo needs to be brought in first. Next, we'll use add in place to combine with this part. We'll select create part in place. We'll save the file first. This is just a practice, so we will name this practice. Then press save and press confirm. Click on this tick for isometric part. This will be our gripper base. We will be placing the gripper on this. After that, let's have a look. Let's go to the top view and turn this around, because we want this gripper base to face downwards. We'll draw on it. We'll draw a triangle by 2 points. When drawing this, we want to cover all of it, because we'll include a servo. So we'll click on this align point and drag out an area. This dimension is approximately 50. We'll make adjustments later. Then we'll extrude this, because this is a 3D object. We will give it a thickness of 2 mm to 2.5 mm. Then press confirm. Once it's done, let's flip this over. It should be more or less like this. We want to center align this object. So we'll go back to assembly mode and center align this. Do you remember how to do it? It's this one, center plane. We need to select 2 planes. This plane and this plane. It's too small, too hard to select. We need to zoom in. We select this plane and then this one. Once you select it, the object will align. This way, this object will be evenly distributed. After that, let's go back to the gripper base. Then right-click the mouse and select Edit, which means Edit in place. Next, I'm going to remove this part of the servo. Let's move on. Next, we need to draw out a frame to fix the servo in place. There's a bar linkage at the side to fix on. We'll do this next. We want it to be aligned. We'll draw a frame. We'll press Ctrl+H to face towards the plane. Next, we'll create a rectangle by 2 points. Press F3 to lock onto plane. Drag it. This height can be adjusted later on, more or less like this. Of course, these lines need to be adjusted later. We draw by approximation first. These 2 edges must be even. So we need to mark these 2 dimensions. We'll set them to 5, press Enter. Then select this, set it to 5 and press Enter. Next, we will offset 2 mm inwards. Then we will draw like segments. To cut off this segment, we'll draw it here. but don't align to the edge. We need to leave out some tolerance, because sometimes the 3D printed objects may not fit our dimensions actually. For the sake of symmetry, if you want this line to be more accurate, we'll use mirror to this midpoint line. Next, train off all redundant lines. We don't need this or this. What's next? We're going to extrude this wall that we just drew. We will extrude an approximate height. There's an object placed here. Where do we place the object? The main reason is because we have the servo to compare to. What is the approximate height we should extrude? It should cover it completely. We press confirm. Since we're using 3D printing, we can actually have dimensions with 0.1 or 0.2, and we don't need to produce this part by hand. If later you want to modify this, you can do so. But since it's 3D printed, the dimensions do not require to be whole numbers. Decimal values are also acceptable. After that, our frame is done. We can then fix the servo onto a frame, so we need to drill holes. Next, we'll click on Project to Sketch. We'll choose this plane, then press confirm. I will select these lines to project. I need to do something here. These two things are overlapping, and it will not be easy to select when extruding. So I will forfeit this action. I will redo this part. I want the projection to be onto this plane, so it is easier to extrude. So we will redo a projection to sketch. I want to project onto this plane, so that it's easier to operate. Press confirm. Then these lines will be projected over. Let's do it again. It was wrong to select face. We should switch to single line option. Then click on the tick. Now you can see the project over here, right? Again, project to sketch, press enter. I want to project to this face. We select this, they are the same. Then we right click the mouse. Then we click on the select tool. This part's progress is up to here. Next, we'll bring out the holes. We'll lock onto this plane. This hole is about 2 mm, so we will complete the circle. Again, circle to the edge, select tool, extrude, pierce through. After drilling the hole, we'll do the rest during the assembly process. Since this will be a 3D printed part, sometimes we think that we don't need it to be that large. Some areas can be gouged out, so we'll carve out the middle part. That is extra. We'll lock onto this plane. We'll create a rectangle by the center. It will be more symmetrical. Remember to move down from the middle and drag this out. Choose a suitable area. This area won't be needed. It will lock onto features automatically, so you need to drag a bit. Make sure the top doesn't exceed boundaries. Press confirm, pierce through. The front is done. The next part is the side. We need to assemble a bar linkage to the edge. Let's move to the side. Again, we need a hole. Select circle and lock on plane. Remember to lock onto point. The first hole we need is 3 mm. Press enter. Let's continue. Maintain the dotted line. Do not let it disappear. You need to draw a circle when the dotted line is showing. Press enter. Regarding the distance between these two holes, let's first set the distance of the hole on the top. Let's set this distance to 10 and press enter. Next is the distance between this hole and this hole. Let's set it to 36 and press enter. Next, we'll extrude this. When piercing through, you can actually pierce it all the way to the other side. It can save us some time. We'll select this and drag this until you see the hole drilled on the other side. Then press confirm. The same with this one, select this and pierce through. You may ask if by piercing this through, will the servo be pierced as well? No, it won't, because they were not part of the same component. They are separate. The sign is done. The two holes are drawn. Let's save the file. You can practice this part. After finished drawing this, let's move on. On these holes, we will draw a protruding disc. Why do we do this? Because it can reduce friction. We let a bar friction with this disc only, so we'll select here. And then draw a circle. Remember to lock on plan. Then align to the center point. And drag a 10 mm hole. The same for this one. This is too close to the edge, but it's alright. If it's like this is too close. So we'll change the length. And move this up a bit. We'll change it to 9. When changing this, pay attention to the arrow. It should be this arrow over here, because we want this to move up. Change it to 9, and press enter. This is linked. We didn't lock this dimension, so remember to lock it. And change it to 36. Press enter and the hole will be adjusted. We probably did something wrong just now. Let's check here. You cannot set this to evenly distributed. We need the hole to move up. So we need to choose the arrow that's next to this hole. This way, the distance 9 will not be modified. Type in 36. And press enter. It will move over. This will be better. Once it's done, we'll extrude this a bit. We'll extrude a length of 1 mm. I just need to elevate this a little bit, so that the whole bar mechanism will not contact the base, and the friction will be smaller. Same here. Lock on plan, lock on center point, 10 mm, and press enter. Same for this, 10 mm. Extrude 1 mm, same for this, select this, we didn't select. Right. Extrude 1 mm. When this is done, we'll save this file. Form this habit. Otherwise, when the computer crashes, having to start over is quite troublesome. You can practice this part. After you finish practicing, since we want to add an ultrasonic sensor here, we are dragging the ultrasonic sensor. Since we're in the synchronized part mode, we'll go back to assembly mode to operate this. We'll click on Insert Component. We'll move to the previous folder. We cannot bring it in. It's alright. We'll go into our folder and operate this. We'll go to our folder and go into the public file folder, then output input module folder. There's an ultrasonic sensor folder. We'll copy it. Then go back to the 11901 folder, because this will be assembled on the lifting mechanism, so we'll place it in the lifting mechanism folder. Let's go back to our drawing area. Click on Insert Component. We'll go back to the previous layer and go into the lifting mechanism folder. Then we'll bring in the ultrasonic sensor. After bringing it in, we want to align it onto this plane. We'll first establish the assembly relationship. We'll select Mate Align. Then select this face that is more protruded and select this plane. After turning over, we need to flip this. Now reverse this direction. We'll reverse this later, it's alright. Click on the Select tool. We can select this object and use the 3D gimbal to roughly turn this around. After that, we need to align the object with this part. We can use the method as before. Click on Assemble, and then select Center Plane. Let's first select two sides, this one and this one. After selecting, we select this plane. it will be aligned. After aligning, next is to align this plane with this plane. But we don't want them to fit align. So this is what we'll do next. You can check this. There's this option in planar align. I will change this to floating. I will let it float. This means that this part and this part will remain parallel. But as for distance, it's up to me to decide when I drag it. Let's select this. And then this, we want this to be floating. Right now, this is parallel. What do we do next? I can move this. Move on select, select this. Then click on move on select. Then drag this. Choose the approximate position that you want. Whether you want it higher or lower, we will choose this position. Once it's done, what do we do next? We need to drill holes. You should be quite experienced with drilling holes by now. Let's do it up to here and you can practice a bit. Once you're finished practicing, we'll move on to the next step, which is to project the holes of the ultrasonic sensor. We'll go to Edit. To modify our gripper base, we'll select Project to Sketch. We first need to confirm the plane to project on. We'll select to list plane. Next, for press confirm, we need to choose the line option. And select this circle, then one over layer. Next, we'll extrude and pierce them through. This is now pierced through. Next, in assembly mode, we'll set the assembly conditions. Let's close this. Assemble axial align. Since we have the parallel condition set here, the condition should suffice after aligning one of the holes. Let's save the file. The 3D drawing is more or less like this. We can create the parts that we need, one by one, like building blocks. After that, what do we do next? We'll do the structural part. Lego uses many parts to make the structure, but we don't. We have two ways of drawing the structure. The one taught in the beginning is more 2D oriented, using board and drilling holes on them. What we are teaching now is more 3-dimensional oriented. After creating it, we can use the 3D printer to produce it. You can practice a bit. Think about this. If you're making such a design, how are you going to produce it? You can practice the part we talked about. After finishing drawing this, because this has sharp corners, it doesn't look good. What we usually do is to make some fillets. We'll select this and add it in place to make some fillets. When we're doing the design, we can guess that the surface will probably be aligned to the surface of the 3D printer. If you add a fillet here, it will be easier when you remove the material of the base. So we always make fillets. Let's make a fillet here. We don't need a big fillet because the board is not very thick. We'll input 0.5 and press enter. We'll use 0.5 to make the fillet in on all edges, and the object will look nicer. We can do it on all this in addition to nice looking effect. It also has an effect on the structure. Compared to having a vertical corner, having a gradual turn around corner actually improves on the structural strength. We'll also make fillets on the protruding discs. After adding fillets on the discs, we are safe the gripper base part. After saving, we can go back. These are the techniques that we often use when we draw this gripper base. You can practice a bit. When it's your turn to draw this, you can do it according to this method. After finishing the practice with the lifting mechanism, we'll begin the assembly between our lifting mechanism and the gripper. The drawing method is the same as we demonstrated before, so we will not show the demonstration of the other structural component. In the lifting mechanism folder, we'll take all this part that we did during practice and place them in a new folder. Use as practice only. During our actual assembly, we'll still provide you with the components already drawn, so that you can assemble them with the components that you made during practice. We'll name this folder Practice. These are the parts used for practice. We'll copy them. Correction, we'll select them and move them in here. Let's go back to the public file folder that was provided to you. Inside the public file folder, there's a ready-made folder. In the lifting mechanism folder, we'll select all of these files and copy them. We'll select the files and copy them. Then we'll go back to the lifting mechanism folder and paste the files in the root folder. We will assemble these components one by one. First, we'll open Solid Edge. Once in, we'll create an isometric assembly. After the isometric assembly file is loaded, we'll bring in the components from the folder. To use, let's go to the lifting mechanism folder. The first thing is the base from the MG90. We'll drag this out. After that, we'll drag in the servo. We're going to perform the assembly. We'll assemble the servo onto the base. We'll select Assemble Axial Align, then select this axis, and align to this axis. After that, because the direction is reversed, so we need to reverse it. This direction is correct now. We move to the next one. Right-click the mouse. Again, Axial Align. Align to this hole. Once it's done, we can move this out a little bit. Actually, we may not need to. This part can allow us to mate align. Select Mate Align. This should be aligned to this outer part. The assembly of this part is complete. Next, let's move on to the next part that needs assembling. For all the structural components, we can click on here and see that the assembly condition of the MG90 lifting base is fixed. So the assembly of the parts will be based on this fixed part. Let's position this vertically, so that's easier to operate. Next, we can bring in one by one each component. Go to the previous folder. We have this bar file. Let's drag this in. Then we click on Assemble, Axial Align, and align to this axis. Select this axis. After that, we'll align the faces. We'll click on Mate Align and select this face and this face. Once this is done, we'll bring in the other bars. Click on the Select tool. We can assemble these two bars first. Select the bar and drag it in. Then click on Axial Align. This axis to this axis. Then Mate Align. Align this face to this face. Same for this one, Axial Align. Axial Align, then Mate Align. Align this face to this face. We need to reverse this. Did we do something wrong? Let's check. Click on it. The face is aligned, but the axis is not. We're to Axial Align again. We'll flip this over. It's alright if we cannot flip it over. We'll move this later. Let's move this. Select it, then click on Move on Select. And then move the gumbo to this point. And then we can rotate this. This rotation will keep the assembly condition, so it's alright. When it's done, we can move on to the next step. We're bringing the other bar. Click on Insert Component. We have this bar used for the servo. Let's drag this in. We will first do axial align. Then we'll do mid align. Here, we need to pay attention to our mid align. This should not be aligned here. Let's undo this. I made a mistake. This face on the servo will actually align with this face. So we need to redo the mid align. We'll click on the select tool, then check this bar. This axial align is correct. For our next action, we need to use mid align to align this face to the other face. It will be embedded. Next, let's take a look at this. We need to rotate this bar because we need to place the servo's rudder inside this groove. Because it will drive this groove, we'll turn it to its front view. Then move the gimbal to this point, and then rotate it. Correction, wrong rotation. It rotated the servo. So let's take a look. Let's try to adjust this. We could not adjust this. When we try to do so, the whole servo will end up rotating, so let's select the MG90 servo assembly. There's an option called Simplified Adjustable. We'll change it to Adjustable Assembly. If we don't do this, it will be considered as a fixed assembly, so the rudder cannot be moved. Let's select this. Then we'll click on Move on Select to adjust it. Select the rudder, and click on Move on Select. Press Confirm, select Object, click on the rudder, and then rotate it into a groove. We just place it in layer for the time being because the alignment cannot be done on a slope. But we can adjust the rudder into a groove first. Click on the Select tool. We can place the rudder in here first. We won't be moving the rudder for the simulation. The assembly on this section is quite special, so we won't adjust this for now. After doing this, we can perform the next step, which is to bring in the gripper base. This is a gripper's base. Let's bring it in. After that, we assemble this through alignment. Align this hole with this hole. Then this to this. Once this is done, we will mid align the faces. Align this face with this face. Then align this face with this face with selected run. Next, we'll do the axial align of this bar. This axis to this axis. Align this with this. When assembling this part, we won't be doing the alignment on the other side. Why not? Because there will be a conflict with this dimension, as you can see here. Because the dimension is not exact, we deliberately made it slightly loose, but it won't be loose in the actual mode. We can still perform simulation at this moment. Let's turn this around to see. We can still make simulation because we have set enough conditions. We'll select drag components to make the simulation. For this simulation, we'll first move this component. We'll select free motion. It's working okay. Each axis has been aligned, so it's good and has no problems. Let's go back to the initial state. When doing the simulation, you may sometimes notice that it will move around. There's a key point here. When doing this overall simulation, we must have a component that's fixed in place, which is our case in this one. Notice that there's an option here. The MG90 lifting mechanism is fixed. You can set this option here. It will be fixed in the 3-dimensional coordinate system and it will not move. So you must pay attention during simulation. Within the components, there must be one. There's fixed. Once this is done, we're going to bring in the servo. We'll click on Insert Component and bring in the servo. Let's drag this in. The servo's rudder is facing the other side. Click on Assemble, Axial Align, then this hole. It's aligned to this hole. Remember to flip this over, and right-click the mouse or Enter. Next is this axis. Which is aligned with this. When it's done, we'll make a line. This face aligned with this face. Our lifting mechanism is almost complete. Next, we're bringing the upper cover for the gripper. We'll go back to the previous folder. There will be a gripper upper cover. This cover will fit in here. We'll use axial align. Whenever it is a circle, we tend to use axial align. It's aligned to this axis. After the axis is aligned, check that it is correct. Next, we'll mat align. This face will align with this face. It's a bit tilted, but it's alright. We'll do planar align. Align this face with this face. But these two faces are not in the same level, so what we will do is to switch it to floating, which means these two faces are parallel. This is okay. The assembly is complete. Let's save the file. This is a first save, so it will ask you to input a file name. So we will name the lifting mechanism assembly. Press save. Once this is done, we will draw the gripper. You can practice a bit and assemble this. You should be quite familiarized with this assembly work. Practice a bit and assemble this. Later we will move on to the next unit, which is the drawing of the gripper. Let's do up to here and let you practice. Next, we will draw the gripper. We will first draw the clouds. We'll click on Create Part in Place and press Confirm. There will be a foam ball. So let's name this ball and press Enter. This will be a sphere. So we can go to solids directly. Select sphere and draw it. We will first select a center point, then drag it out. The current dimension is radius. So if the diameter of our ball is 42, the radius is 21, and press Enter. This ball's radius will be 21. Later during our practice, we'll use this as our target for our gripper. For convenience, we will view this inverted. We'll move this ball by going into assembly mode to move it to a more suitable position. We do it approximately. We can make adjustments later when we are drawing. We'll place it around this position. We'll adjust a more precise location later. Next, we're going to draw the gripper. Let's have a look. What should we draw for this gripper? We'll draw it like this. We'll have our servo driving our gear. Then this gear will drive the other gear. When drawing this gear, there are a few parameters that should be considered. There are a few. The first one is the center to center distance between two gears. The second one is the diameter of the gear shaft, which will determine the size of the screw that you will use on it. Next is gear thickness, how thick the gear's face width will be. There will be other design parameters. We'll discuss it later when we are designing the spur gears. Let's move on. We will be drawing a gripper, like this. Let's go back to this model and look at the same place. First, we'll go to engineering reference. Remember that when doing engineering reference, when drawing the spur gears, we can only draw it in assembly mode. You cannot do it in part mode. Why? Because the spur gear generator will automatically create two spur gears. It is a function in the assembly mode. After selecting it, let's have a look. Once in, we need to modify some settings, because my coordinates origin is different from the default. First, our center to center distance is fixed, so we want the gear number to be adjustable, because we need to determine the module. We talked about module in one of our earlier lessons. What does module stand for? It's the size of a gear. So we will check whether module 1 or 2 is more suitable. We can give it a try. We will leave the strength calculation setting in default. Next is a strength calculation type. We'll let it search for the minimum safety coefficient. Next is a load. We'll set it to torque. The face width will be defined by the user. Press confirm. Once it's done, let's have a look. We don't change the pressure angle. The module is currently set to 3, which is bigger. Let's change it to 2. Regarding the center to center distance, since the space we have here is not large. Based on our measurements from last time, this is approximately 18, so I will input 18. Then press enter. The later part, I will not modify it. I will use the default setting. Next is the shaft's diameter. We'll use a 3mm screws to fix that in place. So the hole in the middle will be 3mm. We can still make modifications later on, but for now we will use 3mm diameter as the initial dimension. This is also 3 for the face widths, because this will be 3D printed. The widths will be 3. The power should not be set too high, or the strength will be too much. Here we will make it more drastic and set it to very low. Let's set it to 1 watt. Set the speed lower. Don't make it too fast or the strength will increase. Our goal is to do one thing, which is to produce this correctly. Once we are done, we'll click on calculate. It shows a calculation failure. Let's see why it failed. The overlap ratio is not within the recommended values. What does this mean? When gears are meshing, when one tooth is leaving the mesh, the next one needs to come in. This is the overlap. It hopes that every time the gear is rotating, each tooth will be meshed. When one tooth is leaving, the next one needs to move in. In what situation will this happen? When the teeth is too big, which means that the module of 2 is too large, so we will lower the module. Let's adjust it to 1.5 because 1 is too small. We don't change anything else. Let's calculate again. We've passed the calculation. Then we can click on create. It will begin generating the gears. We'll give it a name. We can use G, that stands for gear. So we'll name it G1. Next one. The second one is G2, press save. It will be generated. It's not showing. Let's click on them to see where they are. It's aligned to the front. Let's select both gears and use the 3D gumball to move them. Regarding these gears, you need to pay attention to a very important thing. When the gears are meshing, the established relationship is quite completed, so we should not change it. Bear this in mind, or it will take you some time to change it back. That's why it is suggested to move them together. Press confirm. Click on the tick. If there are some assembly relationships that will cause errors, we'll delete them. Next, we'll move this over to this location. Let's start with the first action. Let's check something. Let's see if their assembly relationship includes having them together. Press escape. The first assembly relationship is onto the top view. We don't need this because they need to be at the bottom view, so we'll delete this relationship with the top plane. These three relationships are related to the other gear. This is to align. This is for rotation in opposite direction. And this one is the tangency of the pitch circles. These three relationships are required for rotation. Let's check the next one. It's the same. The other one is the same. Next, we can move this over. Since they already have a merging relationship, so when I move one of the gears, the other one should move alone. First, let's do axial align. Align this axis with this axis. If you can't select it, we can enable this axial alignment option. It is showing now, so we'll move this over. After that, the next step is to align the faces. So we'll do mate align. Then align with this face. Because we want this part to be for alignment, let's have a look. This gear will be under a rudder. You need to pay attention when aligning. The gear is under a rudder. Let's adjust this part. We need to readjust the assembly relationship. This gear will be under a rudder. So we need to mate align this face with this face. Because they already have an assembly relationship, so the other gear will move along. If it doesn't, you need to bring out the pitch circle and establish the tangent, which will take some time, so you need to pay attention that the two gears will move together. Do not destroy the established relationship. After that, we're going to make some adjustments. Let's look at it from the top view. This is already complete. Next, we'll drill a hole on the upper cover. This hole is actually the same as the last one. We have made the same configuration because we did a configuration of its center, so we can use this assembly relationship directly. Because its center to center distance is also 18. We'll align this, there's no problem. We'll do this next. Since there's a small gap, so we will not make the faces mate align. When aligning, we can set this to floating to align them. They will align, but not fit. They will only remain parallel. Once this part is done, let's look at it from this perspective. We're going to perform the next step. The next step is to modify this gear. Because I want to put the rudder in, this action will be more complex, so you need to pay attention when doing this part. Let's do this first. Let's take a look at what we're going to do next. This is what we'll do. We need to design two bars that can perform a gripping action. Let's see how we're going to do this part. Let's select one of the gears. Right-click the mouse and select Edit in place. Once in, we'll see this ordered modeling. When we are drawing, we actually haven't talked about ordered modeling in this course yet. There are two modeling methods in Solid Edge. One is called ordered modeling and the other is called synchronous modeling. What we do is synchronous modeling. Why don't we learn both? It's due to the limited time. If we teach both methods, first, it won't be enough time, and second, I worry that you'll get confused with the commands. That's why we choose synchronous modeling only. We're going to do something first. Next, we're going to draw this crawl. What's more complicated is that when drawing this thing onto the gears are not symmetrical. So we cannot split it in half. That is, they cannot be symmetrical when meshed. When drawing this, both need to be drawn at the same time. Therefore, there's another method to draw this. due to the symmetry problem, let's go back here and see how we're going to draw this. Before we begin our drawing, we're going to draw a sketch. What's the purpose of drawing this sketch? I want to use a sketch to establish the relationship between the two gears, such as the center of center distance, or how to split the gear. All this needs to be drawn in a sketch first. We'll select the sketching plan. Next, I can begin with my drawing. At this point, I can begin drawing the lines, but I need to align to the center point. At this moment, we cannot pinpoint it. Why? In the tools ribbon, there's a same level option. You need to enable it. After you do, when you come back to the drawing, you will notice that you can select it now, which means that the center point and our object are seen as being in the same level. Then we can align the lines with the center point. After drawing the center line, we'll go back to the origin. We can draw a line from this center point. This action is very important. Why? When we're drawing the claws, what can we do? We can use mirror to draw the teeth on both sides. If we don't have this line, since the gears are not symmetrical, there will be a problem. After drawing this center line, we'll change this line to a construction line. It is not a real line. Click it to turn it into a construction line. Then we can begin making our gears. This bolt is not at center, so let's take a look at how to move it. Let's end the current sketch mode and use the select tool to select the bolt. After that, use the 3D gumball to move the bolt to the middle. Move it to an approximation, because when we draw the claw later, its shape will align with the shape of the bolt. When mirroring, the result will be the same. Let's go back here. Once it's done, let's press Escape to finish moving the bolt. Next, we'll select this gear. Right-click the mouse and select Edit. We'll start arranging it. There's no edit. Let's click again. We'll select Edit in place. When editing in place, and the button shows that it is done with order modeling. In our course, we hardly talked about order modeling. All we did was synchronous modeling. Why didn't we talk about order modeling? There are two reasons. First, it's due to the time, that we cannot go over so many lessons. Second, I think that the learning of synchronous modeling is more intuitive. That's why we focused on one of them only. If we learn both at the same time, you may get commands confused. So we use synchronous modeling. Because it is ordered modeling, so we first need to transfer this to the synchronous modeling part. Let's right-click on Array and select Transfer to Synchronous. After transferring to synchronous, notice that the top of the window still shows order modeling. So we need to click on synchronous modeling, and it will switch to this mode. Next, we will act on the gears array. We can grab the lines first. Next, we're going to draw our gears to merge together the gear and the rotor. We'll first lock onto the plane. We'll draw using the line segment tool. Lock on plane. Let's first draw the shape of the claw. We'll first draw a simple claw. Let's give it a claw shape. Drag this over. Let's extend this line a bit. We'll close this first and let it have straight shapes. This line is tilted, but it's alright. We can adjust the line to be vertical. Next, we'll merge together the line segments. After that, we will connect this line segment back to where the gear is. Get a suitable thickness, right-click the mouse to end. Let's drag another line segment back here. At least we need to make the thickness more even. Then this line can be removed using the trim tool. After this section is finished, We can close this contour. We can now close this. It is a closed contour, so we can extrude this. This dimension is 3 mm. We'll input 3 mm and press enter. It will remove material. Why? Because the extrude setting was wrong. We'll select it again. This option should be changed to add material. We want to add material, but it was set to remove. Extrude this to 3 mm, press enter. This closed section is finished. Next, we're going to draw the right side. Let's first close this. Then we will come here to draw. We'll do the same steps from earlier. Select the gear, then go to Edit. After that, we'll right-click on Ordered Modeling and select Transfer to Synchronous. After transferring, we'll select List Array. Check that we're in synchronous mode. We can now begin drawing the line segments. When drawing the lines, we want these lines to move over here for use. What do? We can use the line segment and refer to these lines that are already made. We'll do it from here. In order to draw these line segments, we need them to be on the same level. It's already set, so we can come here and begin our drawing. There's some interference with the point lock on. We'll draw this first. Like this. Make it a closed contour. Actually, don't close it. We'll close it once it's on the other side. After that, we go back to the sketch ribbon and use the mirror tool to mirror this drawn section to the other side. This area was not drawn properly. So let's draw this part again. Remember to trim this line. After that, we're going to use the mirror tool. Press and hold the Shift key. Then select this line segment to serve as the line of symmetry. We'll click from here and move it up. Done. However, this part was not connected well. It's alright, we'll complete it. We should be using this connect tool instead. It's now connected. Then we can come here and close this contour. We'll lock onto this point and connect to here. It's now closed. Next, we can extrude this. Select it, pay attention to it. It will assess this automatically. So we need to extrude this down 3 mm and then press enter. We've completed the design of the claw. We can close and return. The claws are completed. The shape design for the claw doesn't look nice, but it doesn't matter. We'll make detailed adjustments later. We can adjust it by doing the same actions we did earlier. Right-click the mouse and select Edit. We'll add some fillets so that it looks better. We'll go here to the Home ribbon and select the fillet tool. We'll make a fillet at this corner. We can make the size of the fillet larger. Set it to 5 mm and press enter. Same here. Then press close and return. Let's move to the other side. Select Edit. Then the fillet tool, we select here as well. Then close and return. Remember to save the file. We finished the claw part, but we need to add a fixing point for the servo. The servo's rudder should fix onto this part of the claw. We'll perform the next action. After adjusting the rudder's orientation, we'll make a slot to fix the rudder in place. The first thing we'll do is to make this rudder movable. We'll place the gumball at its point and check if we can rotate it. When moving it, the rear part will move alone. It's the same issue. It's a non-movable assembly. So we need to adjust it and change it to a movable assembly. Again, select it and go back to the home ribbon. Click on the Move on Select tool. It didn't move, it's alright. We'll use the Drag Component tool to move it. We'll select the object and choose Free Motion, then rotate this to a position that we want, which is around here. After that, we'll save the file. This will be the fixture position. Next, we need to make a slot at its location. How do we draw this? We can draw our sketch on this plane. Draw a planar sketch, and then extrude it. We can also do it this way. We will first add it in place. Right-click the mouse and edit. Once in, notice that we're in ordered modeling mode, which is incorrect. We need to switch to synchronous modeling because we use the synchronous modeling method. Whenever you notice that your modeling tools are different, it means that you're in ordered modeling mode. The ordered modeling and synchronous modeling modes are different, so we must switch to synchronous modeling. We'll use the Light Segment tool, and we'll lock onto this side. Because I won't add material from here, press Ctrl+H, and define a feature. We want to add on here. We want extrude solid from this plane. So I will draw a closed contour, move it to the side, set this to 6 mm, or 5 mm. 5 mm should be enough. Close it. Select Smart Dimension to adjust the dimensions. When drawing this, we can draw the lines casually. We can later adjust the dimensions so that it fits what we need. The dimensions shown in the CAD software, the sizes are scaled, and it's not the actual size. It should look like this. Next, we'll extrude this. How much do we extrude? We'll extrude all the way to the other side and align with this edge. Let's take a look at this place. This bolt is obstructing our view. Let's hide the bolt for now. Select here. Next, it will move this along. Extrude, remove material and extrude this up. This is done. Next, we need to leave a small frame on this plane. We're going to gouge out a hole in here. We'll use the Light Segment tool, and then press F3 to lock onto a plane. Sketch this lines along this contour. After sketching the lines, we're going to offset inwards, and we're going to give a fixed offset value. We'll give it a 2 mm thickness. Because we're doing 3D modeling now, we can set options here. And we'll select Chain, click on the first line, and then press and hold the Shift key. Once it's done, click on the tick, and you will ask if you want to offset inwards or outwards. Next, we're going to close the contour of what we just drew in order to extrude this section. We'll extrude this section to the back. We can select the Remove Material option. Once it's done, we can place the router in here to drive the claw. We'll go back to the assembly mode. You can try out this part. Next, let's simulate the gripping situation. We hit the ball earlier, so we'll call it back. When performing the gripping action on the ball, we use projection to determine its largest diameter. Next, we're going to determine what height will be the most suitable. We'll use the select tool to move the ball to a more normal height. We'll click on the select tool, then move on select, and select the ball when the tool is activated. When selecting the ball, a 3D gumball will appear. And we can select the axis direction and move it to around this location. Because it will be more precise later when you assemble this onto the vehicle. Let's do the simulation. This is probably the location of where we will grab the ball. Let's take a look at the simulation that we are going to do next. We'll use the close to simulate whether its gripping action can meet our expectations. Let's click on Drag Component and press Confirm. We'll first select the Node Analysis option, since this is currently the first thing testing. So we'll choose Node Analysis, and then select the router that we want to drag. Choose Free Motion, and then move the close. It's more or less like this. This is correct. Next, we can switch to Physical Motion. We'll first select the component that we want to drag. Choose Free Motion. You'll probably wonder, it seems that the rear part will move alone. This is normal. Why? Because it is a movable assembly. Let me show you. Because I'm worried that it's too complex. So we'll switch back to Node Analysis. We don't want the computer's load to be too large. Let's first select the component we want to move, this one. Then drive this vertically. It's close to the position we originally set. Our idea was more or less like this. When you're doing this kind of mechanism design, you first should decide the type of mechanism you're going to use. We can first draft in paper the approximate dimensions that we want. And after confirming the approximate dimensions, we'll then go to the computer for modeling and simulation. If it's okay, we can then draw the structural components and place it in the actuators, such as the motor or the servo, then add in one by one the movable mechanism parts. Then we'll use simulation to check whether the action performed and its height conforms to our ideas. Once this part is finished, let's save this file. Next, we're going to assemble this lifting mechanism that we designed onto our vehicle. You can try doing this simulation part. Once we finish practicing, we'll bring in the vehicle assembly that we drew last time. We placed the file in our folder in the desktop. Let's go to the desktop to the 11901 folder, where I placed every file. There is a vehicle assembly file. Open it. There are some components missing. Why are these some components missing? That is because these components used during our practice, they are actually not needed anymore. It's alright, we'll not care for them now. We'll close this window. Let's first remove these components, because they were already assembled during our practice, so we can remove this. We have no need for them anymore. Let's delete them. We'll save the file again. This is our vehicle assembly. The components that we removed were the leftovers of our practice last time, and were used for drafting practice. We can now formally bring in the lifting mechanism from earlier. Let's go into the lifting mechanism folder and drag in the lifting mechanism assembly. Once dragged in, we're going to assemble it. When assembling, we'll use axial align. Because this is inverted, So this hole should align with this position. At this moment, you cannot select it, so we need to activate component. Once it's done, it's still inverted, so we'll reverse it. Then right-click the mouse to confirm. When this is done, we'll axial align the other hole. This axis should align with this axis. The position is correct. Let's do the next step. We'll mat align. This face should align with this face. It's placed. Return to the back view, which turns to its side and have a look. This is the mechanism we met in our practice. It's more or less like this. You can practice assembling them together, while also removing the components from last time. After this assembly is completed, let's try and simulate its action when it's assembled onto the vehicle. We'll click on Drag Component and press Confirm. We'll choose Node Analysis and select the component we want to drag. Notice that we cannot select it. Why can't we select it? That's right, if you're experienced, you'll probably understand why. We'll select this and right-click the mouse in here. When our secondary assemblies are brought into the main assembly, the default setting is that it's non-movable because we don't want it to move and cause some issues. After we bring them in, we'll adjust the parts that we want to set to movable. Instead of bringing in the secondary assemblies and having them all set to movable, we need to change this assembly to movable. After changing the setting, we'll click on Drag Component and press Confirm. Node Analysis. Select the object to drag. Now it's possible to select it. Choose Free Motion. We can move this up and down. We can also move this ball, also in this mode. Undo this and select the ball. Because I don't want it to be moved off, so we'll choose Linear Motion. Its axis is set there, so we'll move it to this position. Place it at a location where it's aligned with the plan. Let's move on to the next one. Let's go back here. We need to click on the Select tool first. Otherwise, when you click on Return, the location of the ball will be modified. Click on Drag Component and press Confirm. At this time, we can perform Physical Motion Analysis. In this mode, it will tell you where there's an obstruction. This mode will consume more resources. So if your main assembly becomes more and more complex, it is not recommended to perform Physical Motion Analysis on the main assembly, because it will take more time to analyze, and it will consume more resources. This part is probably stuck. If it cannot move down, it means that an object is obstructing it, which means that it's the ball that's placed there when performing physical motion. In a way, it is assessing what happens in real life. It consumes a lot of the computer resources. Let's go back to the right view and adjust this. We switch back to Node Analysis. And again, choose this component to drag. Let's move this to the position it should be, around this position. At this moment, do not press Return because we want the ball to remain in this position. Let's do this again since it got stuck last time. This time it should not happen. We'll switch to Physical Motion. Let's explain again. When it's performing Physical Motion Analysis, it needs to do calculations, so it will take some time. Let's move this down. It may get stuck, so let's save the file. I worry that if it crashes, I will need to start over and it will take some time. Let's click on Drag Component. Again. Let's select these components that we are going to drag. Move this up and down. Let's try it with Node Analysis. This is normal. It's because this rudder will interfere. I did not move this rudder to its actual position. It should be fixed in here. You need to establish an assembly relationship. What happened just now is probably due to the router's interference, and that's why they couldn't move. For this, we can perform assembly. You can try this out if you are interested. I will ask you to practice and adjust this part, and also try out the physical motion analysis. Once the design of the mechanism and structure of our robot is finished, we still need to check whether there's any interference between our mechanism components. What is interference? It means that there are two components overlapping in the same space, which is an unreasonable situation. During our drawing process, we may forget or omit it, so we need to use computer software to do this. Let's take a look at this. Let's use our lifting mechanism to do this part. We need to go to the inspect ribbon. There's an inspect interference tool. It will automatically inspect our interference. As instructed in the hint bar, you can click or frame select several components, so we'll frame select them. When selected, we'll click on the tick. After that, we'll click on process and check which part has any problem. It will be displayed in color. The parts have interference issues in this space. There might be two components overlapping, so remember to adjust and fix them. This state is unreasonable. We need to fix this. There's an assembly problem here. This is because I set this to be a tight fit, so it will be assembled tightly. These remaining sections are not reasonable. This is an assembly issue. This gear section is not reasonable. After finishing with the assembly, remember to inspect for interference and see whether this is caused by our design or by the assembly. You can try out this function. After finishing the design or our robot, what we need to do next is its production. The production can be divided into two parts. The first one is handcraft production, which is the traditional method. After we print out our design drawing, we proceed with the production based on the marked dimensions marked on the design drawing. Another method is to convert this into a digital file and use this digital file for the laser cutting machine or the 3D printing machine to produce what we want. And then perform the assembly of such components. After completing our preliminary design, we carry out simulation to confirm the feasibility of our design, then produce it into a real object. To confirm, now we're going to output its engineering drawing. To create an engineering drawing, there's an option called isometric. Engineering drawing. Once inside, the first function that we will use is this view wizard. We'll click on the view wizard when selecting. We'll use the model that we drew the first time, which is the chassis. Please pay attention to the file that we are opening. It can be an assembly file, but we'll use a part file, change this to part, and then open the lower chassis file that we drew on our first time. Once in, you notice that this is not the view we want, because we want the front view. This is not front view, so we need to change it. Because when we started drawing, our position was different from default setting. We can select this view wizard and redefine what we want. Once in, there is also a 3D view cube at the lower right corner. We'll click on it if we want this view to become the front view. We'll confirm and close, then go to the button and press confirm. Next, we'll be given this. We can use the mouse's scroll wheel to scale this and see what size we want. Once it's done, we have this front view drawing. Then we can have the top view and the right view. In the end, you're provided an isometric drawing. We'll place it here for a reference. Once it is done, what do we do next? Click on select. At this time, they're actually linked to one another. Once it's done, we will mark the dimensions. The marking method is the same as what we learned during our first year in senior high school. In principle, the dimension marking is placed between the drawings. Here, for example, because there are fillets present, we can use the edges for markings. Next is the hole size. When marking the dimensions, do not place them inside the drawings. You must place them outside the drawings. You must follow this principle. Next is the distance between this edge and this edge. Then fillet, which is the same for all. After marking the dimensions one by one, let's keep on marking. If your fillet size is unanimous, then you don't need to mark them one by one, because by looking at the drawing, we can know from the marking that it is the same for all of them. We also need to mark their relative position. The distance between this hole and the ones adjacent to it. This must be marked, because if you are going to make this by hand, you need to have this marked, otherwise you won't be able to know how to produce it. This dimension that we marked, we accidentally marked the fillet, so we need to delete it. It's more or less the dimension markings. A lot of dimensions are symmetrical. If it's symmetrical, then we can leave it out and you can reference the dimension on the other side and calculate yourself. Once the marking is done, what do we do next? We'll export it. Click on Save As. When saving, it will be saved as an engineering drawing file. We'll click on Save. In this file, as we have explained to you before, when managing our files, I said to you in the beginning that the main assembly will be placed in the root folder. The secondary assemblies and parts will be placed in respective folders. The advantage of this is that if a student is responsible for drawing the chassis, he only needs to copy all the files in the chassis folder that he needs. He doesn't need to copy all the files. Other students may have to draw their own parts. For example, someone may need to continue with the drawing of the control system. As long as you discuss and confirm the mutual assembly of each secondary assembly, you can do each part separately. This is the reason why we do file management. If you don't do this, it will be difficult to divide the work. You can practice the making and output of the lower chassis engineering drawing. After finishing the parts engineering drawing, we'll demonstrate the making of the engineering drawing of an assembly. In the same manner, we'll go to Create and select Isometric Engineering Drawing. We'll choose a mechanism. We'll first click on View Wizard and choose our controller. The controller assembly is in here. Press Confirm. Let's choose something more special. Let's use a chassis assembly. Press Open. Remember that we are choosing an assembly file. because I'll be explaining about the assembly file. Open the file, put a morning, cannot find the controller assembly. Choose the wrong file name, press open. First, we'll first go to the view wizard to readjust the orientation of the view. We select the customized view and choose the view we want. This position, let's rotate it. Let's set it to this position, then close it. Then press confirm. We'll drag this in. It can also show the top and right views. If you want to outline, you can do so. It seems that it won't fit. Let's press escape and do it again. We'll adjust it. Let's redo it. Click on the view wizard and select the chassis assembly. Then click on view wizard, select customize view. Select the position we want. Let's choose a smaller size, or it won't fit, because our top view will be quite large. Place the right view, and then the isometric view. Next, let's have a look. This is the most important thing. When we're making an engineering drawing, especially for assemblies, I will make a parts list. Why do we need a parts list? The reason is that we have many parts. And when we need to account for the parts for statistics or stack up, checking from the drawing actually takes a lot of time. So this function can show all the parts used in the assembly in a single table, as well as indicating the quantity used. The hint bar will instruct us to select the drawing view. We'll choose this one. Next, a frame will appear, and we'll left-click the mouse. Let's zoom in. The name of all, the parts used and quantity will be shown. We have the motor assembly, one lower chassis, one bull eye wheel. For the copper pillars, double female ends 25. We'll need 4 of them, and for copper pillars, double female ends 30. One upper chassis. This is quite convenient for statistics. Also, on the drawing view, we clicked. You'll notice this. Let's select it. It will mark each item number and quantity. So this function is quite convenient when used in assembly files. It will speed up the process. You can practice this part about the engineering drawing output for assemblies and the making of the parts table. Hello everyone. What we're going to do next is the export of 2D and 3D files. What we'll perform next is to export the drawing file used for laser cutting processing. Let's take a look at this. This is the export of 2D files. We'll first create an engineering drawing file. We'll click on the view wizard. In this case, we can only choose a part file. Earlier we used the lower chassis for demonstration, so now we'll use the upper chassis instead. Press open. After opening the file, we can select the drawing. View layout. We'll select customize view and choose the plane we want. We'll use this one and press close, then press confirm once in. We just need one drawing only, because we only need to laser cut this drawing. What's special about it is that when we convert this into a DXF file, we do not just use the save as method directly. We must perform this action first. we'll right-click the mouse and select Draw in View. In this Draw in View mode, because it is in a 2D drawing state, then you select Save As. It will then let you choose the file format you want. The formats often used are, for example, the DXF file. We'll select it and press Save. It can then be converted. Let me explain it to you again. In this engineering drawing mode, you need to right-click the drawing and select the Draw in View option in this Draw in View mode. Select Save As. Only then you can choose the DXF file format. The dimension properties will also be converted alone. That's why we chose this. You can practice this part. Once the laser cutting file is converted, we'll teach you how to export 3D files next. Let's open an old file. What we mostly need are in the lifting mechanism folder. Why do we need to use 3D? Because you can make more unique shapes and curves with 3D. So it will be easier to use 3D printing for this part. We'll select the MG90 gripper base and press Open. We're going to print this part. We'll click on the application icon, and there will be a 3D printing option. After clicking, we can preview. There are some surfaces which are probably unavailable in Time 1. We'll select this part. Before exporting the file, we need to check one thing. What is the unit we're using? We have an option here. Click on it to check this. This action is very important. The unit that we're exporting must be in mm. The default unit is in inches, so need to convert it to mm. You must pay attention to this part. After confirming that the exporting unit is in mm, we'll press Confirm. Next, we'll click on Export. When exporting, we'll type in the file name, choose the STL file format and press Save. You can practice how to operate this.